The Kuiper Belt feels like the solar system's outer wall until you realise it's barely the doorstep. Beyond it may lurk the Oort Cloud, a cold, unseen swarm stretching so far it could reach nearly halfway to the nearest star. If our edge of the solar system is just the entrance, where does our neighbourhood actually end, and what exactly is hiding out there? The outer solar system is not a frontier you reach. It is a frontier that keeps receding as your sense of scale breaks. What looks like a boundary becomes a corridor, and the corridor opens into something the eye cannot hold. For centuries, we have drawn the solar system like a tidy family portrait. Planets in a row, distances politely squeezed until they fit. That picture comforts us because it implies an ending you can point to, a last orbit and then blank space. But space does not end cleanly, and distance is not just geometry. It is an eraser, stripping warmth, light, and certainty with every additional unit outward. Out there, the sun's authority changes character. Close in, it is obvious. Bright days, fast years, gravity that feels absolute. Farther out, the same force becomes statistical, an influence measured in probabilities, in slow nudges, in orbits that take lifetimes to complete. And somewhere beyond the places we have photographed, the solar system stops behaving like a collection of worlds and starts behaving like a faint, enormous field. This film is about two regions that share a name in our imagination, the outer edge, yet belong to different kinds of reality. One is a frozen wilderness we can chart object by object, where small bodies keep the scars and chemistry of early time. The other is a hypothesis with teeth, a structure too remote to image directly, known mainly through messengers that arrive unannounced, briefly brilliant, and then gone. To compare them honestly, we have to rebuild the map from first principles. We have to feel what an astronomical unit means when sunlight is already thin, and what it means when even time becomes a distance. We have to watch Neptune act less like a destination and more like a gatekeeper, shaping routes, trapping bodies in resonant patterns, and scattering others into long exile. We have to accept that empty space is not empty at all, but sparsely populated in ways that preserve history. We will travel through the Kuiper Belt as it truly is, thick, scattered, and dynamic rather than a neat ring, then confront the shock of seeing it up close. A world once treated as a footnote becomes a landscape with weather of a different kind, with exotic ices that behave like rock and rock that behaves like mountain. And when the camera leaves that encounter behind, the story does not end. The light simply grows weaker, and our evidence becomes subtler. Because the farther we go, the more the solar system speaks through indirect signatures. Comets become couriers, tiny nuclei carrying outer chemistry inward and orbital clues outward. Their paths are not just spectacle, they are data, and their statistics point toward a reservoir that cannot be explained by a simple disk. That reservoir, if it exists as our models suggest, changes the meaning of the word edge into something colder, a boundary you infer, not one you see. And then comes the terrifying comparison, not as a single number, but as a shift in scale so large it rewrites intuition. The Kuiper Belt is a place where exploration feels imaginable, where a probe can still send back postcards. The Oort Cloud, by contrast, is a realm where the sun's grasp becomes fragile, where passing stars and the galaxy's tide can reach in and rearrange what we thought was ours. It is less a shoreline than a fading ownership, an immense dim shell whose very existence is argued from the behaviour of bodies that visit us only briefly. So where does the solar system actually end? At the last photographed world, at the limit of solar wind, or at the farthest bodies still bound, barely to the sun? To answer, we will follow the evidence wherever it leads, from crisp images to statistical shadows, and from confident labels to definitions that fail under pressure. What begins as a comparison of two distant regions becomes a more unsettling investigation into how we draw boundaries in a universe that prefers gradients. By the time we reach the farthest human signals, thin radio whispers crossing a darkening gulf, we will see why the solar system's edge is not a line. It is a slow dissolve, shaped by diminishing light, widening distance, and the quiet pull of the galaxy itself. And in that dissolve, the difference between the Kuiper Belt and the Oort Cloud is not merely large, it is transformative, a scale change that forces us to rethink what home even means. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by dismantling the familiar planetary diagram, then move outward through Neptune's sculpting gravity into the Kuiper Belt's living archive. From there, we follow comets and fading spacecraft signals into an unseen domain where the solar system becomes a hypothesis written in motion. We learn the solar system from a picture that fits on a page, and the page feels like a promise. The planets line up like beads, evenly spaced, with Pluto parked at the edge like a final punctuation mark. That diagram is useful for names and order, yet it trains a comforting lie about distance. It suggests the outer solar system is a final neighbourhood, not the beginning of a wilderness. To break that lie, we need a scale that refuses to cooperate with our instincts. The inner planets collapse into a tight cluster, and the outer planets stretch into long, cold gaps that swallow attention. The real story is not where things are drawn, because drawings hide the emptiness between them. The real story is how far apart they actually are, and how long light and spacecraft take to cross those intervals. Even sunlight changes character as distance grows, and that shift is visible if you know what to look for. At Earth, the sun is bright enough to cast hard shadows and heat dark surfaces quickly. Farther out, the same sunlight thins with the inverse square law, fading as 1 over distance squared. By the time you reach Neptune, sunlight is roughly a 900th of what Earth receives, and the solar system looks like twilight at noon. Astronomers use a unit built for this problem, because ordinary numbers become a blur. 1 astronomical unit, or AU, is the average distance from Earth to the Sun, defined precisely in modern standards. It is about 150 million kilometers, and it is already too large for intuition to hold. In the outer solar system, miles and kilometers become noise, because the digits pile up faster than meaning. AU keeps the numbers readable, and it keeps the comparisons honest across huge spans. It also anchors distance to something familiar, because Earth's orbit is our reference rhythm. When you hear 30 AU, you can translate it as 30 Earth, sun gaps laid end to end. That is still abstract, yet it is a clean abstraction, and clean abstractions are how astronomy stays sane. On that AU scale, Neptune orbits at about 30 AU, circling the Sun once every 165 Earth years. Pluto's average distance is about 39 AU, and even that number hides an eccentric orbit that swings inward and outward. At its closest, Pluto can drift inside Neptune's average distance, although resonances keep them from colliding. If Pluto feels impossibly far in our mental map, it is because we are still thinking in classroom proportions. The shock is that Pluto is not the end of anything, even in the most generous emotional sense. Pluto is a signpost near the start of the first false ending, a marker that our old diagram runs out of paper. Beyond it, the solar system does not become simpler or emptier in a clean way. It becomes stranger, more statistical, and more dependent on gravity's long reach. Here is the first scale trap, and it catches almost everyone at first glance. If you place the Sun at the centre and mark Neptune at 30 AU, you have not even reached the region where leftover building blocks dominate. Past Neptune, the planet's spacing gives way to a broad reservoir of frozen worlds, many too small and dark to notice. That reservoir is the Kuiper Belt, and it is less a ring than a population. The idea has a history because science often begins as a suspicion before it becomes a catalogue. In the mid-20th century, astronomers such as Gerard Kuiper argued for icy remnants beyond Neptune, although the modern belt is broader than early sketches. The concept also grew from dynamical puzzles, especially the supply of short-period comets. If comets return on predictable schedules, something must be storing them, and something must be nudging them inward. The classical Kuiper Belt extends to roughly 50 AU, occupying a thickened disk near the plane of the planets. Beyond that, related populations continue in different orbital families, and the boundary becomes a debate, not a line. Some objects are scattered outward by Neptune after close gravitational encounters, and their elongated orbits carry them far beyond the classical region. Others are trapped in resonances that keep time with Neptune's orbit, like gears that never quite disengage. Resonance sounds poetic, but it is a strict mathematical lock. Pluto itself is in a 3.2 resonance with Neptune, completing 2 orbits for every 3 Neptune makes. That timing prevents close approaches, because the geometry repeats in a protective pattern. The Kuiper Belt is filled with similar clocks, and those clocks preserve evidence of how the giant planets migrated early on. The point is not one exact cutoff, because nature rarely respects our tidy categories. The point is that the solar system does not end at Pluto, and it does not even end at the Kuiper Belt's neatest definition. What changes is the density of objects, the kinds of orbits, and the energy of sunlight. The farther out you go, the more the solar system becomes a set of probabilities rather than a list of worlds. The Kuiper Belt is a deep freeze archive of planetary formation, and archives matter because they keep records that inner regions erase. It holds dwarf planets, small icy bodies, and debris that never assembled into a full planet. It includes contact binaries, where two lobes touch like a slow-motion collision that never finished. It includes surfaces that can preserve ancient chemistry, because sunlight is weak and impacts are infrequent. This is planetary science, with the thermostat turned down, and the cold preserves delicate structures. At tens of AU, water ice behaves like rock, and exotic ices become the active materials. Methane, nitrogen, and carbon monoxide can freeze onto surfaces, then sublimate when seasons change. Even a thin atmosphere can appear and collapse as a world tilts, rotates, and drifts along its long orbit. For decades, the Kuiper Belt was a hypothesis supported by dynamics and a few detections at the edge of telescope sensitivity. Early discoveries in the 1990s turned the idea into a growing census, and each new object widened the map. The belt helped explain why Neptune has the orbit it does, and why comets arrive with certain periods. Yet for the public imagination it remained mostly a phrase, a dim band beyond Pluto. Then a spacecraft turned it into a place, and places change how we think. New Horizons launched to reach Pluto, and it carried our curiosity beyond the old map with a single fast trajectory. It travelled for nearly a decade, crossing the orbits of the giant planets like a needle threading a dark fabric. Along the way, it reminded us that distance is time, and time is the price of exploration. In 2015, New Horizons transformed Pluto from a dot into a complex world with geology, atmosphere, and active processes. The flyby revealed bright plains of nitrogen ice, mountains of water ice, and hazes layered in a thin sky. It showed that even far from the sun, internal heat and volatile chemistry can sculpt a surface. Pluto stopped being an argument about definitions and became a landscape. Visually, the change is almost unsettling, because the mind has to update its file. A point of a light becomes a globe with a limb, then a world with shadows, then a place with textures. The camera frames glide across heart-shaped Sputnik planitia, and the brightness looks too alive for such cold. In that moment, the outer solar system stops feeling symbolic and starts feeling inhabited by processes. New Horizons did not stop at Pluto, because its momentum was part of the plan. It continued deeper into the Kuiper Belt and flew past Arrokoth, a small object shaped like a gentle merger. Arrokoth looked like a relic that never got reheated, never got rebuilt, and never got erased. Its two lobes met at low speed, preserving a contact seam like a fossilized embrace. Arrokoth's surface, faintly reddish, hints at complex organic molecules altered by radiation over billions of years. Its shape suggests that early building blocks could assemble softly, in a calm region with low collision speeds. That matters, because it supports models where planets grew from pebbles and clumps, not constant violent impacts. It was evidence that the Kuiper Belt contains pristine leftovers from the solar system's earliest assembly. It also delivered a warning that the word far is relative to the true scale. Even after Pluto and Arrokoth, we were still close to home by the solar system's full dimensions. We had reached a frontier of discovery, but not the frontier of the sun's reach. The map had expanded, yet the emptiness beyond still dominated the frame. This is where the documentary's engine starts to turn, because scale is not a trivia fact. Cosmic scale changes what we mean by frontier, by edge, and by the word outside. It changes what feels reachable, and what feels like a different category of space. When we say the solar system ends, we have to decide what we are measuring, and why that measurement matters. Are we measuring planets because they are bright and memorable in a lineup? Are we measuring small bodies because they are the leftover mass and the historical record? Are we measuring magnetic influence because it shapes charged particles and space weather? Or are we measuring gravitational reach because gravity is the sun's most durable signature? A second boundary often gets mistaken for the finish line, partly because it comes with a dramatic name. Voyager 1 crossed the Heliopause and entered interstellar space, and headlines called it the moment we left the solar system. The heliopause is real, and it is dramatic because it is a collision of pressures. It is where the solar wind's outward push yields to the interstellar medium pressing back. The solar wind is not just a breeze, but a continuous outflow of charged particles from the sun's corona. It carries the sun's magnetic field outward, twisting it into a spiral as the sun rotates. As it expands, it cools and thins, and eventually it slows when it meets resistance. That slowing region, the termination shock, is part of the heliosphere's layered structure. The heliopause itself is the boundary where the sun's plasma influence gives way, and Voyager's instruments felt that change. Particle counts shifted, magnetic fields altered, and the spacecraft crossed into a region dominated by galactic particles. It was a milestone for physics because it turned a theoretical boundary into a measured environment. Yet it was never a clean border for ownership, only a border for wind. The heliosphere is a weather system, not a property line, and weather systems move. It is shaped by the sun's activity cycle and by the surrounding galactic environment, which is not uniform. It can expand and contract over time, and it is not centered on the planets. Crossing it tells us we have left the sun's immediate plasma influence, which matters for radiation and space conditions. It does not tell us we have left the solar system's gravitational territory, because gravity fades slowly. The sun's mass still dominates the motions of distant objects far beyond the heliopause. Even in regions where the solar wind is irrelevant, the sun can still hold a comet in a long, fragile orbit. That distinction between plasma bubble and gravitational domain is where the confusion lives. If the Kuiper Belt is the first false ending, the heliopause can be the second. Both are boundaries we can talk about, and one we can even cross with a probe. Yet neither boundary answers the deeper question that keeps returning. How far does the solar system really extend when gravity is the last authority? To approach that question, we have to confront a structure we cannot photograph directly because it is too sparse and too dark. It does not glow, and it does not reflect much light because its members are small and distant. It is not a belt in a plane, and it is not a ring around the sun. It is a vast, hypothesized cloud of icy bodies, arranged more like a shell than a disk. It is called the Oort Cloud, and even the name carries the feel of inference. Jan Oort proposed it in 1950 to explain the distribution of long-period comet orbits, which seemed to come from all directions. The hypothesis was elegant because it turned randomness into geometry. A roughly spherical reservoir would naturally send comets inward from any angle. The Oort Cloud is inferred, not mapped, and that difference should make us cautious and curious at once. Its evidence arrives as visitors that appear without warning, brightening as they fall toward the sun. Long-period comets come in from every direction, not just along the plane where the planets orbit. Their path suggests a distant reservoir that is roughly spherical, because their source is not confined to the ecliptic. The Oort Cloud is the simplest explanation that fits those trajectories, and simplicity is a kind of power. Without it, we would need many separate sources arranged in an unlikely pattern. With it, we can connect comet statistics to a distant population shaped by gravity over billions of years. The cloud becomes a hypothesis you can test indirectly by counting and modelling the comets we see. In this story, comets are messengers from the dark carrying ancient ice into sunlight. Some are short-period comets tied to the Kuiper Belt and its scattered populations, returning on humanly trackable schedules. Others take thousands or millions of years to return, if they return at all. Those long-period comets imply starting points far beyond the Kuiper Belt, where orbits are weakly bound. They imply a storage zone where the sun's gravity still holds, but only barely, like a hand at the edge of a reach. A small nudge can change everything, because orbital energies are tiny out there. A passing star, a molecular cloud, or the slow pull of the galaxy can perturb an object. Once nudged, an icy body can begin a long fall inward, becoming visible only near the end of its journey. The scale difference is the terrifying part because it turns our familiar map into a local inset. The Kuiper Belt's classical region reaches to around 50 AU, and even generous definitions stay in the hundreds or low thousands of AU. The Oort Cloud's outer boundary is often placed near 100,000 AU, though the number is uncertain and model-dependent. That is not a small extension, but a leap that changes the solar system's shape. At 100,000 or AU, the sun's gravity is a thin claim on distant ice, and the environment is no longer purely solar. Passing stars and the Milky Way itself can tug on those orbits, adding a slow chaos to the system. The galactic tide, the gentle gravitational field of the galaxy, can reshape the cloud over time. It can nudge objects inward, turning stable storage into a pipeline of comets. It can also strip objects away, blurring the boundary between what belongs to the Sun and what belongs to the galaxy. In that regime, the solar system is not an island with cliffs, but a shoreline with shifting sandbars. The Sun moves through the galaxy, and its distant cloud moves with it, always under competing pulls. The edge becomes less a circle and more a negotiation. This is why the edge becomes a philosophical problem as much as a scientific one. The solar system is mostly empty space, mostly dark, and mostly defined by things we cannot see directly. Its boundaries may not be clean, because gravity does not switch off at a sign. They may fade into the interstellar medium, where the Sun is only one mass among many. The frontier is not a wall, and it is not even a fence. It is a gradient, a slow thinning of influence until other influences matter more. That gradient forces a question that feels simple but is not. At what point does our solar system become the galaxy, and who gets to decide the threshold? The comfortable map avoids this because it has to, and because it is designed for teaching. It compresses billions of kilometers into centimeters, and it keeps the story focused on planets that can be drawn as circles. That compression hides the real hierarchy, and it hides the true emptiness that defines space. The planets are a bright inner detail, and they occupy almost none of the volume. The Kuiper Belt is a dim outer neighborhood, populated but sparse, with worlds that rarely meet. The Oort Cloud, if it exists as predicted, is the dominant volume of the solar system, a vast shell that dwarfs everything inside it. In that picture, the familiar planets become a central spark, and the solar system becomes mostly potential. It becomes a gravitational idea expressed across an enormous distance. So the tension is set, and it is meant to unsettle the viewer's inner scale. Pluto is far, but it is not the frontier, and it never was. The Kuiper Belt feels like an ending, but it is a doorway into a larger architecture of remnants. Voyager 1 feels like an escape, but it only crossed a bubble, leaving gravity still in charge. Beyond all of that may be a shell of ice that stretches toward the nearest stars, shaped by the galaxy's pull and punctuated by comets that fall inward. Those comets are not just spectacles, but evidence that the solar system is porous at its edges. They remind us that the Sun's domain is not sealed, and that the galaxy can reach into it. The abyss is not empty, but it is thinly populated, and that thinness is part of its mystery. We're going to compare two structures that sound similar but are not, and the difference matters. One is a flattened belt of known objects with measured orbits and direct spacecraft encounters. The other is a vast unseen cloud inferred from dynamics, comet statistics, and the subtle mathematics of gravity. Their difference in scale is not just large, but transformative, because it rewrites what the phrase outer solar system is allowed to mean. Next, we step into the Kuiper Belt itself and treat it as a place with architecture. We trace its boundaries, its resonances, and its populations, and we ask why it looks the way it does. Only then can we feel the full shock of what comes after, because context is what makes scale real. Only then can the Oort Cloud stop being a name and become a looming plausible abyss. Neptune is not the last planet in a lineup, and it is not a decorative endpoint on a classroom poster. Neptune is the first gatekeeper of the deep outer system, an icy giant whose gravity organizes space long after sunlight stops feeling familiar. Out here, the sun is still dominant, yet its warmth is diluted into a pale, distant glare. At about 30 astronomical units, Neptune's orbit marks a shift in how the solar system is structured and how it remembers itself. Inside that boundary, planets dominate the narrative with frequent encounters, bright sunlight, and comparatively rapid change. Outside, small bodies and long-term gravity start writing the record, and they do it with a patience that feels almost inhuman. Neptune's gravity does not merely tug on objects as they pass, because the important work happens through repetition. It sorts them, shepherds them, and sometimes ejects them into stranger paths, using repeated nudges rather than a single dramatic shove. Over millions of years, those nudges accumulate, tiny changes in speed and timing that become a new orbit. In physics terms, each encounter trades energy and angular momentum, and the trade is often subtle enough to miss in a single snapshot. A body arrives with one orbital period, leaves with another, and the difference can be a fraction of a percent. Given enough passes, that fraction becomes destiny, and the map of the outer system slowly redraws itself. To picture this, imagine Neptune moving through darkness like a heavy ship through thin ice. The ship does not touch every fragment, yet its wake still rearranges the field, leaving lanes, clusters, and gaps. In celestial mechanics, that wake is written in resonances, scattering events, and stable zones that can endure for billions of years. When we say wake, we are really talking about phase space, an abstract landscape of possible motions. In that landscape, some paths are smooth and protective, while others are chaotic and easily disrupted. Neptune carves both kinds, and the difference determines whether an object becomes a long-term resident or a wandering exile. The Kuiper Belt begins as a region, not a ring, and that distinction matters for how we visualize it. It is a broad, thickened disk of icy bodies beyond Neptune, with overlapping neighborhoods rather than a single sharp boundary. The belt is not a line you can draw with confidence, because its populations blend into one another in both space and history. We call it a belt because it sits near the planetary plane, roughly aligned with the solar system's original disk. That word can mislead, because it suggests a dense band like Saturn's rings, bright, crowded, and constantly colliding. The Kuiper Belt is something else, a sparse frontier where the dominant experience is separation. Saturn's rings are crowded and collisional on short timescales, and their particles can meet again within hours or days. The Kuiper Belt is slow, thin, and spread across volumes so large that nearby becomes a relative term. Even when objects share the same region, they are often isolated by distances that dwarf the scale of planets. Typical Kuiper Belt objects are not neighbours in any human sense, even when their orbits occupy similar ranges of distance. Many are tens of millions of miles apart, and many are separated by far more than that, drifting along paths that rarely bring them into proximity. If you could stand on one of these bodies, the sky would not look busy, it would look empty. That emptiness is not a footnote in the story of the outer solar system, because it controls how often anything can happen. It is the dominant physical condition, and it changes what collisions, evolution, and even geology can look like. In a crowded environment, frequent impacts erase old surfaces, remix material, and reset the clock. In the Kuiper Belt, the clock can keep ticking without being smashed, and that makes the place feel like a preserved layer of time. In the inner solar system, impacts grind surfaces down and stir the chemistry, and they do it often enough to blur the earliest record. In the Kuiper Belt, encounters are rarer, and the past can remain legible, sometimes preserved in shape, sometimes in orbital architecture, sometimes in the distribution of ices. The region behaves like an archive where the pages are not constantly torn out, although the ink is faint and the shelves are far apart. Even the smallest crater can be a meaningful timestamp, because it may not be overwritten for eons. The question becomes unsettling. How much history can survive simply because nothing comes close enough to erase it? The belt's architecture starts with the classical Kuiper Belt, a population that occupies roughly 42 to 48 AU in relatively stable, low eccentricity orbits. These objects tend to avoid close approaches to Neptune, and that avoidance is the key to their long-term survival. Stability here is not a guarantee of calm, but it is a guarantee of persistence. Classical objects are not perfectly uniform, and their inclinations can be modest or surprisingly tilted relative to the planetary plane. Some remain in a colder, flatter component, while others occupy a hotter, more inclined distribution that hints at early stirring. Their stability makes them valuable as a baseline population, something like a control group for the outer solar system. That hot and cold language is dynamical, not thermal, and it describes orbital excitation in plain terms. A cold population keeps low inclinations and modest eccentricities, as if it was never strongly disturbed. A hot population carries extra tilt and stretch, implying that something, migration, scattering, or resonant pumping, shook the disk early on. Beyond the classical region, the Kuiper Belt blends into resonant populations, and resonance is where Neptune's gatekeeping becomes most visible. These objects are locked into orbital rhythms with Neptune, repeating patterns of alignment that keep them safe or keep them constrained. In a system ruled by gravity, timing can be as protective as distance. Resonance is a timing relationship that repeats geometry, and it does so with mathematical precision. If an object completes a certain number of orbits for every set number of Neptune's orbits, Their relative positions cycle through a repeating sequence. That repetition can prevent close approaches, and it can preserve a pattern for billions of years, even as everything continues moving. The most famous resonant object is Pluto, and its fame once made it seem like an exception. Pluto is in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of Neptune, and that ratio is not an aesthetic coincidence. It is a dynamical arrangement that shapes Pluto's entire identity. That resonance functions as a safety mechanism, a kind of celestial scheduling that prevents dangerous encounters. Pluto's orbit is eccentric and inclined, and it can cross Neptune's orbital distance, which sounds like a recipe for collision. Resonance ensures they're never in the same place together, because the timing of their closest approaches is controlled. If you could watch from above the solar system's plane, you would see a choreography that repeats. Neptune returns to certain longitudes, Pluto returns to others, and the moments when their paths could intersect are precisely the moments when they do not. The result is stability built from repetition, an orbit protected by rhythm. The protection is not mystical, and it is not fragile because the resonance also locks the angle of Pluto's perihelion relative to Neptune. That geometric lock keeps Pluto far away when it crosses Neptune's distance, and it does so cycle after cycle. The deeper point is sobering. Order can emerge from gravity alone, even in a wilderness. Pluto is a dwarf planet because it does not clear its orbital neighbourhood, and that phrase carries a specific dynamical meaning. Clearing is not about vacuuming space clean, and it is not about being alone. Clearing is about gravitational dominance, whether a body is massive enough to scatter, accrete, or otherwise control most objects near its orbit over the age of the solar system. Pluto shares its zone with many bodies, and it is part of a population rather than the ruler of a region. That is why it falls into the dwarf planet category, even though it is round, differentiated, and geologically complex. The definition can feel like bureaucracy, yet it reflects a real distinction in how mass is distributed. A planet tends to outweigh and outmuscle its neighbours, leaving behind a dynamically clean path. A dwarf planet can be impressive in its own right, yet it lives among peers and cousins that remain gravitationally relevant. In the Kuiper Belt, that difference matters, because the neighbourhood itself is the story. Pluto is still dynamically significant, and its resonance class defines a whole family of objects called Plutonos. These worlds trace Neptune's influence in a way that is both subtle and unmistakable, because their orbits carry the same rhythm. When we map Plutonos, we are mapping the reach of Neptune's long-term gravity. Neptune's resonances are like grooves in phase space, paths in the mathematics of motion where objects can linger. A small body that drifts into the right orbital period can become trapped, and once trapped, it can be carried along as Neptune's own orbit changes. This is one of the clearest clues that the solar system did not always look like it does now. This points to migration, the slow rearrangement of the giant planets after they formed. The giant planets did not necessarily form exactly where we see them now, and their movement reshaped the small body map. Migration is not a sprint across space. It is a gradual shift that can still have dramatic consequences. As Neptune migrated outward, its resonances swept through the primordial disk like moving nets. Some objects were trapped and transported, preserving a fossil of that motion in their present-day orbital periods and eccentricities. In this sense, resonance is not just a current condition, it is a historical record. The record is written in ratios and angles, and it is surprisingly durable because orbital architecture can outlast surface features. A crater can be erased, a frost layer can migrate, but a resonance can persist for the age of the solar system. That invites a deeper question. Are we reading a population, or are we reading an event? Other objects were not trapped, and their story is rougher. Some were scattered by close encounters with Neptune, gaining elongated orbits that reach far beyond the classical belt, and those encounters could happen in a cascade. A single close pass can change an orbit, but repeated passes can transform it completely. This is the scattered disk, a population with high eccentricities and perihelia still influenced by Neptune. These objects swing inward toward Neptune's realm, then arc outward into deep space, taking hundreds or even thousands of years to complete a single orbit. Their paths feel like long exiles that still remember the planet that expelled them. In visual terms, they are comets in waiting, although many may never visit the inner system at all. Their orbits are stretched like rubber bands, with a brief, fast passage near the Sun and a long, slow drift at aphelion. The geometry itself feels like a sentence, an outward fling that never fully breaks the connection. The Kuiper Belt, then, is partly a family name, and that family includes overlapping branches. It includes the classical belt, resonant groups, and the scattered disk, and the boundaries between them are not always clean. The region is less like a single neighbourhood, and more like a set of districts that bleed into one another. These categories are not just labels for a catalogue, and they are not merely a convenience for astronomers. They are evidence that gravity sculpted the region rather than leaving it as a uniform debris field. When we see gaps, clusters, and resonant piles, we are seeing the fingerprints of long-term dynamics. The horror of the Kuiper Belt is not monsters or storms, and it is not the cinematic horror of sudden violence. The horror is the scale of emptiness and the patience of orbital time, an environment where nothing happens quickly, yet everything is always moving. It is a wilderness measured in AU and in centuries. A body can circle the Sun for centuries without coming close to anything, not because it is hidden, but because the space between objects is enormous. Its nearest neighbour can be so far away that even a bright flare would go unseen, swallowed by distance and the inverse square fall-off of light. In this region, isolation is the default condition. Close encounters are rare because the volume is huge and the objects are small, and that combination makes intersection unlikely. The belt is a wilderness where most trajectories never cross, and where even a near miss can be separated by millions of kilometres. The geometry of space itself becomes a protective barrier. That barrier is statistical as much as it is physical, because the belt is not a packed swarm. The average object occupies a vast personal volume, moving through it like a lone aircraft over an ocean at night. You can search for hours and see nothing, and then a faint point appears, barely brighter than the noise. When collisions do happen, their speeds can be low compared to inner system impacts, and that difference changes the outcome. Low speeds matter because they allow gentle accretion instead of total destruction, especially when the bodies are porous and icy. A slow collision can merge two objects rather than shatter them into fragments. One of the clearest signatures of gentle accretion is the contact binary, a shape that looks like two worlds pressed together. A contact binary is two lobes fused together, like a slow merger that never separated, preserving the moment of assembly. Instead of a cratered sphere, you get a double-lobed silhouette, an object that advertises its origin. Contact binaries imply that some building blocks met softly, not violently, and that their relative velocities stayed small. They suggest a cold environment where gravitational gathering could proceed without constant disruption. In a region where impacts are rare, the few that occur can leave unusually clear signatures. This is not a quiet place in the emotional sense, because the distances and timescales can feel unsettling. It is quiet in the mechanical sense, and that quiet can preserve primordial shapes that would not survive closer to the Sun. The Kuiper Belt can keep artifacts of formation that the inner solar system has largely erased. A contact binary can keep the outline of early assembly, and it can retain details that look almost anatomical. It can preserve a seam, a neck, and a mismatch in lobe sizes that records its formation, as if two separate histories were welded into one body. When we see such a shape, we are seeing a relic of the earliest building process. The Kuiper Belt is also a chemistry lesson written in ice, and the cold is not merely a background condition. At around 40 Kelvin, water ice behaves like rock, supporting cliffs and mountains, and resisting flow on human timescales. In plain terms, the stone of this region can be frozen water. That temperature changes what counts as bedrock, and it changes what counts as an active ingredient. In the Kuiper Belt, water ice can be structural, while more volatile ices act like mobile materials that can migrate, frost, and retreat. The landscape becomes a layered system of different freezing points and different behaviours. Nitrogen, methane, and carbon monoxide can freeze onto surfaces, forming bright deposits and smooth plains. They can also sublimate even under weak sunlight, reshaping terrain over time by moving mass from one place to another. In an environment this cold, even a small change in temperature can decide whether an ice is stable or transient. Sublimation is not dramatic like boiling water, and it does not require liquid to exist. It is slow mass transfer, driven by seasons and sunlight, and it can still move landscapes by carving pits, collapsing surfaces, or depositing fresh frost elsewhere. The process is quiet, but its cumulative effects can be large. Thin atmospheres can appear and collapse on some worlds, built from the same volatiles that frost the ground. A small change in solar heating across an orbit can shift where volatiles settle, and that shift can rearrange surface brightness and texture. In the outer system, an atmosphere can be a temporary state rather than a permanent feature. Even the light itself behaves differently here, because the sun is a brilliant star rather than a dominating disk. Shadows sharpen, contrasts deepen, and the sky can turn inky black even at midday. When frost migrates, it does so under a low distant lamp, enough energy to matter, yet never enough to feel warm. This is why the outer solar system is not automatically dead, even when the sunlight is faint and the temperatures are extreme. Cold slows many processes, yet volatility can keep surfaces changing, and change does not always require heat in the familiar sense. Sometimes it requires only time, a slight tilt, and a material willing to move. The Kuiper Belt also holds evidence that planet building continued far from the Sun, beyond the region where the major planets formed. Pluto is not alone, and it is not the largest, and that realization arrived gradually. For much of the 20th century, Pluto looked like a solitary outpost, but the sky had more to reveal. The idea of a distant belt was proposed long before it was confirmed, and it carried the name of Gerard Kuiper, who discussed the possibility of a reservoir beyond Neptune. Later work refined the concept, and observations finally began to populate it with real objects. The belt was not discovered in a single moment. It emerged as a pattern as surveys improved. In the 1990s, sensitive CCD detectors and systematic searches finally began to catch the faint drift of distant bodies. Each detection was a whisper, a moving pixel against a crowded starfield, and it demanded nights of confirmation. The result was not a single headline, but a slow revelation that Pluto had company. Eris was discovered in 2005, and it is comparable to Pluto in size and mass, orbiting even farther out on a more distant inclined path. Its existence forced a confrontation with the word planet, because it made Pluto's uniqueness harder to defend. If one Pluto exists, why not many? And what does that do to the category? If Pluto is a planet, then Eris pressures the definition, and it does so with uncomfortable logic. If many Pluto-like bodies exist, then the solar system contains a class, not a single exception, and classification must reflect that reality. The debate was not only about Pluto, it was about how we describe a system that keeps surprising us. The debate led to the dwarf planet definition, formalized to separate dynamical dominance from physical roundness. A dwarf planet is round from self-gravity, orbits the Sun, and has not cleared its neighborhood, meaning it shares its orbital zone with comparable bodies. The definition is imperfect, yet it captures a real difference in gravitational influence. That definition can sound abstract, so it helps to translate it into plain language. A planet tends to be the main architect of its orbital region, while a dwarf planet is a significant resident among many. The difference is not about beauty or complexity. It is about who controls the local traffic. Haumea and Makemake joined the list, each with its own clues and contradictions. Haumea's rapid rotation stretches it into an elongated shape, and its collisional family hints at violent events even in the cold. Makemake's bright surface and volatile retention show that composition and sunlight interact in subtle ways, producing worlds that resist simple expectations. Their discovery also expanded the perceived boundary of the solar system in the public imagination. The map did not end at Pluto, and it did not end at one dwarf planet, because each new detection implied many more unseen bodies. Every discovery was a reminder that our census is incomplete, and that the outer system is bigger than our catalogues. Yet discovery is still a thin slice of reality, limited by distance, brightness, and the size of our telescopes. We have detected only a fraction of Kuiper Belt objects, biased toward brighter and nearer ones, and toward those that pass through regions of sky we survey most often. The belt we know is shaped by our methods as much as by nature. Most KBOs are too small and dark to see easily, and many are known only as faint points that drift against background stars. Their sizes can be uncertain, their shapes unknown, and their orbits incomplete until years of tracking refine the arc. In the Kuiper Belt, even identifying an object can be a long-term project. Even when we know an orbit, we often do not know the object itself, and that gap matters. We infer diameter from brightness, then guess albedo, then revise everything again when a better measurement arrives. A dark object can masquerade as a small one, and a bright icy surface can make a modest body look larger than it is. The Kuiper Belt is therefore both a catalogue and a blind spot, a place where we name populations while barely sampling their physical diversity. We can map orbital families with confidence, yet we still struggle to describe what most members look like up close. That mismatch between dynamical knowledge and physical ignorance creates a productive tension. This uncertainty matters for the central question because it sets the stage for what comes next. If the Kuiper Belt already defies intuition, then the Oort Cloud will break it, expanding scale beyond what feels reasonable. The belt is our first lesson in outer darkness, and it is not the last. The Kuiper Belt feels like an edge because it is the farthest region we've explored up close, and human perception treats the farthest known as the boundary. That feeling is powerful, and it is misleading, because the solar system does not end where our close-up images stop. The edge is a psychological artifact, not a physical wall. Neptune's resonances make the belt look organised, yet the organisation is partial and still not fully explained. There are gaps, clusters, and boundaries that need interpretation, and each one could encode a different chapter of early history. The belt is structured, but it is not tidy. Some of those boundaries may reflect migration history, and some may reflect how the primordial disk was truncated. Some may reflect how objects were lost, scattered, or never formed in certain zones, leaving a drop in density that persists. When we see an edge, we have to ask whether it is a true limit or a sculpted absence. The belt's outer edge near 48 to 50 AU is especially suggestive because it looks like a sudden thinning of material. That drop may record an early limit in the distribution of solids, or it may record later depletion by dynamics that preferentially removes certain orbits. Either way, the edge behaves like a clue rather than a conclusion. Even the emptiness has structure, and that structure can be read like a coded message. The distribution of inclinations, eccentricities, and resonant occupancy encodes the solar system's early rearrangement, including how strongly the disk was stirred and how far Neptune migrated. The belt is sparse, but it is not random. This chapter is about entering that wilderness with the right expectations, because the wrong metaphor will distort everything. We are not approaching a crowded ring, and we are not approaching a uniform debris field. We are approaching a sparse archive, where the most important feature is often what is missing. We are also approaching a place where definitions become unstable, because the objects do not fit our old categories neatly. Planet, dwarf planet, belt, disk, scattered population. These are tools, not truths, and they are revised when new data arrives. In the outer system, language has to remain flexible. Pluto sits at the centre of this tension, both scientifically and culturally. It is small compared to the major planets, yet it is a gateway to the belt's complexity, and it forces us to confront the difference between dynamical status and physical richness. Pluto is not the end of a story, it is the beginning of a larger one. For decades, Pluto was treated as a lonely outpost, a single name at the edge of the map. The Kuiper Belt reframed it as a member of a vast population shaped by Neptune, and that reframing changed what Pluto meant. Instead of an odd planet, it became a representative, one example among many. Then a spacecraft arrived, and the story changed again, because proximity changes what questions we can ask. New Horizons turned Pluto from a dynamical symbol into a physical world, with textures, layers, and weather-like cycles. The flyby was brief, yet it was enough to shatter the old image of a frozen relic. The approach images sharpened from a point of light into a disk, and then into a landscape. The flyby revealed geology that should not have been there, at least by older expectations built around cold and distance. It revealed volatile plains, water ice mountains, and atmospheric haze, features that imply ongoing processes. You can imagine the camera's view tightening, frame by frame, as the pixelated dot becomes a world with a horizon. Subtle colour differences emerge, ruddy tholins, pale frosts, and bluish shadows that hint at texture. What looked like a single tone from Earth becomes a mosaic under a low sun. Pluto was not a dead ice ball waiting at the edge of the map, and it was not a static museum piece. Pluto was active enough to force a re-evaluation of what cold worlds can do, and active enough to raise questions about energy sources, internal structure, and the mobility of volatile ices. If this world can change, what else has been underestimated? That re-evaluation does not stop at Pluto, because Pluto is only one sample from a vast region. If Pluto can be complex, then other Kuiper Belt worlds may be complex in different ways, shaped by different mixtures of ice, rock, and volatile chemistry. The belt becomes less like a graveyard and more like a laboratory. The Kuiper Belt becomes a testing ground for the solar system's outer physics, where weak sunlight, low temperatures, and long timescales intersect. Here, the usual intuition about geology and atmosphere has to be recalibrated, because the materials and the rates are different. The same laws apply, but they express themselves in unfamiliar ways. It is also where the documentary's scale argument gains traction, because the belt is vast compared to planetary distances we casually discuss. Yet it is still a small preface, a comparatively thin zone around the Sun when measured against what may lie farther out. The belt feels infinite, but it is not the full footprint. The Kuiper Belt is the first false ending because it looks like the edge on a handheld map. It is actually the doorway to something far larger, and it trains us to distrust our sense of completion. When the map ends, the system does not. Next, we follow the New Horizons thread deeper into Pluto's story, using that close-up to recalibrate what the frozen wilderness can contain. We treat Pluto not as a label in a resonance diagram, but as terrain under a low sun. We let the details, textures, contrasts, and subtle hazes reset our expectations, and as we do, we keep the central question in view, because scale is the quiet antagonist of this chapter. How can this sparse belt feel infinite when it is only the inner rim of the Sun's reach, and only the first major reservoir beyond the planets? What does it mean to call something empty when it contains more history than we can read? Because beyond Neptune's gatekeeping and beyond the Kuiper Belt's overlapping neighbourhoods, the solar system's true footprint may still be waiting in darkness. That darkness is not empty, and it is not a supernatural void. It is simply too thin, too far, and too slow for easy certainty, which is why it can feel like horror. We have entered the Kuiper Belt's frozen wilderness, and we have learned to see emptiness as a physical condition with consequences. The next step is to confront its most famous world as a place, not a dot, and to measure what cold really allows. From there, the scale comparison will sharpen, and the looming unknown will take its proper shape. The Kuiper Belt will become a measured region, and the Oort Cloud will become the looming unknown, not as a metaphor but as a problem of distance, time, and detection. The gatekeeper has done its work and the archive has opened, but the darkness beyond still waits to be defined. New Horizons reaches Pluto in 2015, and the Kuiper Belt stops being theoretical distance. The flyby is brief, yet it rewrites expectations about what cold worlds can do. Pluto shifts from a debated label to a geologic actor with motives. The central question tightens because the images refuse to stay simple. If complexity thrives here, what hides farther out? For decades, Pluto was a point of light, a faint dot that drifted against background stars. Its existence began as mathematics, when Percival Lowell searched for a planet X to explain perceived orbital irregularities. Those irregularities were partly measurement error, yet the search itself shaped astronomy's imagination for a generation. Clyde Tombaugh found Pluto in 1930 with a blink comparator, 2 glass plates, 2 nights, 1 moving speck. The method was brutally manual, and it depended on patience as much as optics. For most of the 20th century, that speck carried a cultural weight far larger than its measured size, and textbooks treated it as the 9th planet by default. Then, as better measurements arrived, Pluto's mass shrank, and its status became contested. The discovery of Charon in 1978 was a turning point, because it allowed Pluto's mass to be measured through orbital dynamics rather than guesswork. Later, improved detectors and surveys revealed other Kuiper Belt bodies, some comparable in size, which made Pluto look less singular. The 2006 IAU definition of planet did not change Pluto's surface, yet it changed the public story. New Horizons arrives after that debate, and it brings a different kind of authority. Close-range truth that does not negotiate with tradition. Even before Encounter, telescopes hinted at seasons and surface contrast. Pluto's brightness changed over time, and its spectrum showed methane bands that waxed and waned. Those spectral bands are fingerprints, because molecules absorb light at specific wavelengths, and methane's pattern is especially distinctive. Occultations, when Pluto passed in front of a star, revealed an atmosphere by the way starlight dimmed gradually instead of snapping off. The gradual fade implies refraction and scattering in a thin gas, and it also constrains pressure at the surface. Still, those were indirect clues, like hearing a landscape through a wall. The approach images sharpen week by week, and the old mental file collapses. A world appears with plains, mountains, and a layered sky, and it looks less like a relic than a system. In the visuals, the first resolved disk is small but unmistakable, with a pale patch that grows into a heart. As the spacecraft closes, the heart gains texture, and the surrounding terrain fractures into distinct provinces. Shadows at the limb become readable, and the terminator line, day sliding into night, reveals relief through the lengthening of shadows. The camera does not merely confirm Pluto's existence, it introduces Pluto as a place with weather, geology, and time. Sputnik Planitia dominates the encounter as a bright, heart-like basin of volatile ice. It reads as a reservoir, a trap for nitrogen, carbon monoxide, and methane. The basin sits like a smooth plate inset into rougher country, and its brightness is not just colour. Brightness means reflectivity, and reflectivity means temperature control, because a lighter surface absorbs less sunlight. That feedback matters on a world where every watt counts, and where a few degrees can decide whether nitrogen is gas or solid. At New Horizons resolution, Sputnik Planitia looks young, with few obvious impact scars. The plane is not merely coated with frost, as an early guess might have assumed. It is structured, patterned, and apparently mobile, with polygonal cells that resemble a frozen quilt. The cells are kilometers across, and their boundaries often trace subtle troughs that look like the seams of slow motion. Along the edges, the smoothness breaks into lobes and tongues. Those forms look like flow, and the mind reaches for glaciers. Except the material is not water. The key material is nitrogen ice, which behaves strangely at Pluto's temperatures. Pluto sits near 39 AU, where sunlight is weak and equilibrium temperatures hover around a few tens of Kelvin. In plain language, it is so cold that familiar materials stop behaving familiarly, and the phase diagrams that govern them become the real map. Nitrogen's melting point is far below water's, and its solid phase is mechanically soft. Under Pluto's modest gravity, nitrogen ice can deform and flow over geologic time. It can act like a glacier, even when the landscape feels unimaginably frozen. This is not magic, but rheology, how materials respond to stress. Ice is not a single substance in behaviour, because ice is a category of solids with different crystal structures, impurities, and temperature-dependent viscosities. For nitrogen, a small increase in temperature can lower viscosity dramatically, making creep more efficient. Pressure matters too, because the weight of overlying ice increases stress at depth. When a layer is thick enough, even slow deformation becomes inevitable. On Pluto, slow still means motion that reshapes a basin over millions of years, and that timescale is fast by planetary standards. Water ice plays the opposite role, and that contrast becomes the chapter's hinge. At Pluto temperatures, water ice is rigid, strong, and effectively rock-like. Its viscosity becomes so high that it can support steep relief and resist flow for long intervals. New Horizons sees mountains rising several kilometers, some with sharp ridgelines and blocky faces. Those peaks are consistent with a water ice crust behaving as bedrock, fractured by stress rather than rounded by melting. The landscape becomes a materials lesson, where chemistry decides what is mountain and what is glacier. In the visuals, the mountains cast long, blue-grey shadows across adjacent plains. Their slopes look jagged, as if broken rather than melted, and their bases meet smoother deposits like islands meeting a sea. The narrator can linger on the paradox because it is the point. The bedrock is water, and the mobile veneer is nitrogen. On Earth, water carves rock. On Pluto, nitrogen carves water ice rock. And the roles reverse without changing the underlying physics. Glacial flow on Pluto is driven by pressure, slope, and slow thermal conditions. Nitrogen ice can creep under its own weight, especially where it thickens in basins. Even small temperature gradients can change viscosity and flow rate, so the difference between sunlit and shaded slopes matters. The basin's topography funnels ice into low points, and the low points thicken the ice further. That is a feedback loop that makes Sputnik Planitia not just a deposit, but a machine that organises motion. Convection is plausible if the nitrogen layer is thick enough and warm enough at depth. Convection is a simple idea with large consequences. Warmer, less dense material rises, cooler material sinks, and the surface is renewed. On Pluto, warm still means extremely cold by Earth standards, yet relative differences can drive motion. Heat can leak upward from the interior, and sunlight can warm the uppermost skin, creating gradients that matter over long time. The polygonal patterns in Sputnik Planitia hint at cells and renewal. The exact mechanism remains debated, but the geometry invites the hypothesis. If convection is happening, it would erase craters by overturning the surface. That would make Sputnik Planitia look young even if it has existed for a long time. The cells would be the visible skin of a deeper circulation, like slow boiling in a pot that never reaches liquid. The question becomes quantitative, because science demands numbers. How thick is the nitrogen layer, and what is the temperature gradient through it? New Horizons provides constraints, and models attempt to close the gap by testing viscosities, heat flux, and plausible layer thicknesses. The basin itself raises deeper questions about why the volatile reservoir sits where it does. Sputnik Planitia may be an impact basin that created a low, cold trap. A large impact would excavate material, depress the crust, and leave a topographic bowl. Bowls collect volatiles, and volatiles brighten the bowl, and brightness cools it further. That is an elegant explanation, and it matches what we know about cold trapping on other bodies, from the Moon's poles to Mercury's shadowed craters. Yet it is not the only explanation, and Pluto rarely offers single-cause answers. Sputnik Planitia may also represent a mass anomaly that reoriented Pluto, shifting the basin toward the tidal axis. True polar wander is one candidate explanation, not a settled fact. The logic is subtle. If a region becomes denser, the spinning body may reorient to place that mass closer to the equator. On Pluto, the presence of Charon adds a tidal preference, because the system has a gravitational geometry. The point is that geology, ice physics, and global dynamics intersect here. One bright basin becomes a clue to the whole planet. Around the basin, New Horizons finds signs of transport and deposition. Nitrogen glaciers appear to spill into adjacent terrain, filling valleys and embaying older surfaces. Flow fronts and lobat margins suggest slow movement rather than static frost, and their edges sometimes look scalloped, as if the ice repeatedly advanced and paused. In some places, the ice seems to pool behind ridges, as if it is dammed by higher ground. Elsewhere, it threads through gaps like a viscous fluid, choosing the easiest path, and the terrain reads like a frozen drainage network. The plains meet rugged blocks that look like broken crustal rafts. Some interpretations treat them as water ice fragments floating in denser nitrogen ice, because water ice is less dense than solid nitrogen under relevant conditions. If that density contrast is correct, the blocks could behave like icebergs, tilting and clustering as the nitrogen moves. The image is striking, and it tempts certainty, because it resembles familiar sea ice dynamics in an alien key. The uncertainty must remain explicit because remote geology is a discipline of constrained imagination, and every analogy has limits. Pluto's surface also shows pits, troughs, and textures consistent with sublimation and collapse. Volatile ices can sublimate directly into gas under weak sunlight, skipping the liquid phase entirely. Over time, sublimation can carve depressions, undermine layers, and leave behind a lag deposit of less volatile material. That lag can be darker, which increases absorption and accelerates local loss. Another feedback loop. Deposition can then smooth surfaces again, resetting the visual clock. This is outer solar system geology driven by phase change, not by liquid water rivers. In the visuals, the pits look like dark pores in a pale skin, sometimes aligned, sometimes scattered. Their edges can appear sharp, suggesting that the material is removed faster than it can relax. Nearby, streaks and subtle colour changes hint at different ice mixtures or grain sizes, and those differences can alter thermal behaviour. The camera's oblique lighting makes small slopes visible, and small slopes matter on a world where flow is slow. Pluto teaches patience because its processes are measured in epochs, and because the evidence is written in textures rather than motion. Above the ground, Pluto surprises again with an atmosphere that is thin but structured. New Horizons measures a nitrogen-dominated atmosphere with trace methane and other species. The surface pressure is tiny compared to Earth, yet it is enough to carry haze and to shape thermal structure. Temperature profiles inferred from radio occultation and ultraviolet measurements suggest layers, inversions, and a complex balance of heating and cooling. The atmosphere is not a permanent blanket. It is a seasonal system that can expand and collapse as Pluto moves along its eccentric orbit. Pluto's seasons are extreme because of its axial tilt and long year. Its spin axis is highly inclined, so sunlight can favour one hemisphere for decades. Its orbit is also eccentric, so the distance to the Sun changes substantially over a Pluto year. As sunlight shifts, nitrogen frost can sublimate from one hemisphere and condense on another. That exchange can thicken the atmosphere or nearly freeze it out onto the surface, turning air into ice and ice back into air. Models predict partial collapse near aphelion, though timing and magnitude depend on thermal inertia. Thermal inertia is the surface's resistance to temperature change, and it depends on grain size, porosity, and layering. A fluffy, porous surface warms and cools quickly, while a denser slab holds heat longer. That difference determines whether nitrogen stays gaseous through a long winter or condenses into a global frost. The key idea is mobility, because even at the edge of sunlight, volatiles still cycle, and a small energy imbalance can move a planet's atmosphere. The haze layers become one of the flyby's most consequential clues. New Horizons sees multiple distinct haze strata extending high above the surface, stacked like faint smoke rings. The hazes likely form when ultraviolet light and charged particles break apart methane. The fragments recombine into more complex hydrocarbons and nitriles, building larger molecules step by step. Those particles coagulate, grow, and settle, tinting surfaces and altering albedo. Over time, they may form tholins, complex organic residues that help explain Pluto's reddish-brown regions. In the visuals, the limb of Pluto glows with a delicate blue arc. Above it, thin bands appear, dozens of them, each one a boundary between slightly different atmospheric conditions. The layers suggest waves and stability, as if the atmosphere is quietly breathing. Gravity waves can propagate upward from winds moving over terrain, and even weak circulation can organize haze into bands. Weak sunlight still drives chemistry, and chemistry still reshapes appearance. The haze is not decoration. It is a record of ongoing reactions. This photochemistry links Pluto to a broader outer solar system theme. At tens of AU, the Sun is faint, yet photons still arrive in vast numbers. Over long timescales, even low flux can build complex organics, because time substitutes for intensity. Radiation processing can darken and redden surfaces across the Kuiper Belt, producing the colours telescopes detect as subtle slopes. Pluto is a close-up case study of processes we infer elsewhere from colours alone, and it warns us not to mistake redness for simple dirt. The chemistry also raises a quiet question about surfaces as archives. If haze particles settle out for millions of years, they can form a thin mantle. That mantle can insulate ice beneath, change reflectivity, and influence where volatiles migrate. In other words, chemistry can steer geology, and geology can then expose fresh ice for chemistry to work on again. On Pluto, the link is visible in colour boundaries and in the contrast between bright volatile plains and darker, older terrains. The planet becomes a laboratory, where sunlight, even diluted, still has leverage. Pluto's atmosphere also interacts with escape and space weather. Some molecules can reach high altitudes and be lost to space over time, especially lighter species and fragments produced by photochemistry. The escape rate measured by New Horizons was lower than some pre-flyby predictions. That forces revisions to how quickly Pluto's volatiles are depleted, and it changes how we imagine the planet's long-term evolution. The atmosphere is fragile, yet not instantly transient, and that nuance matters for any world that sits near the boundary between holding and losing gas. Escape is not just a loss term, because it also shapes composition. If certain molecules escape more readily, the remaining atmosphere can become enriched in heavier species. Meanwhile, the solar wind interacts with the upper atmosphere, and Charon may intercept some escaping material. The system becomes coupled, with Pluto's air feeding a region of space around both bodies. New Horizons samples that environment as it passes through, turning invisible interactions into measured curves, and turning speculation into constraints. The flyby also reframes Pluto's interior as an active participant. A small world should cool quickly, and old expectations assumed geological death, yet the surface looks young in key regions, implying resurfacing within the last few 100 million years. Crater counts are the main tool, comparing impact density to modelled Kuiper Belt impact rates. The method has uncertainties, because the impactor population is not perfectly known, and because small craters are easier to miss. Still, the relative youth stands out because some terrains are cratered and others are not. Counting craters is a discipline of careful bias. Lighting angle can hide shallow craters, and smooth deposits can bury older ones. Secondary craters, formed by ejecta from a larger impact, can complicate statistics. Even so, when a region as large as Sputnik Planitia shows a striking scarcity of craters, the simplest inference is renewal. Something has been resurfacing it, and it has been doing so recently in geologic terms. The planet refuses to be a fossil, and that refusal becomes the chapter's underlying shock. Internal heat is the simplest energy source that does not require sunlight. Pluto contains rock as well as ice, and radioactive isotopes in rock produce heat as they decay. Radiogenic heating declines over time, yet it can persist for billions of years, especially if the rock fraction is substantial. An ice shell can insulate the interior, slowing heat loss to space, and a layered structure can trap warmth where it matters. If antifreezes like ammonia or salts are present, they can lower freezing points and delay solidification, keeping liquid stable at temperatures that would otherwise freeze. Under the right conditions, a subsurface ocean becomes plausible. The phrase ocean can mislead, because it suggests waves and open water. Here it means a buried liquid layer, sealed beneath kilometers of ice, kept warm by internal heat and insulation. Such a layer would influence how Pluto flexes and fractures, and it would change how the crust responds to loading. It could also help explain why certain tectonic features appear where they do, because an ocean decouples the shell from the deeper interior. An ocean is not claimed as a certainty, but as a coherent explanation for multiple observations. A liquid layer can help explain tectonic features and global stress patterns, because freezing and expansion create extensional stresses. It can also support the idea of reorientation if a mass anomaly is compensated at depth. The thickness of the ice shell and the ocean's persistence depend on composition and heat flow. The key is that Pluto is not automatically frozen solid forever, even if its surface looks like winter made permanent. Charon enters the story as context for Pluto's thermal and tidal history. Pluto and Charon form a binary system, locked in mutual synchronous rotation, always showing the same faces to each other. That configuration is rare among planets, yet common among tidally evolved pairs. Many models suggest they formed from a giant impact early on, when the outer solar system was still assembling. That event would have generated enormous heat and likely melted large fractions of Pluto's outer layers, setting the stage for differentiation and long-term internal structure. Tidal evolution would then dissipate energy as the system settled into its current configuration. As Pluto and Charon exchanged angular momentum, their rotation slowed and their separation increased. During that process, internal friction would convert orbital energy into heat. Even if tides are quiet now, the past could have left long-lived consequences, including a differentiated interior and a reworked crust. The binary is not just a companion story, it is part of Pluto's memory, written into its shape, its orbit, and possibly its interior. The surface offers candidate signs of cryovolcanism, though interpretation remains cautious. Features like Wright Mons and Picard Mons have been described as possible cryovolcanic constructs. They are broad, mountainous rises with central depressions and hummocky textures. Their scale is enormous compared to terrestrial volcanoes, and their slopes are gentle, consistent with viscous, icy materials. If they are cryovolcanoes, they imply that Pluto once moved material from inside to out, perhaps as slurries of water ice mixed with volatiles. Alternative explanations exist, including tectonic uplift and erosion by sublimation. A central depression could be collapse rather than a vent, and hummocks could be blocks rather than flows. The responsible narration keeps the options open while explaining why the hypothesis exists. The key observation is morphological. The features look constructed rather than purely eroded, and they sit in a landscape that otherwise offers few obvious sources of such large-scale relief. Pluto invites competing models, and the data constrain them without always deciding. Resurfacing could also occur through convection in volatile ices. If Sputnik Planitia's nitrogen layer convects, it can recycle the surface and erase craters without dramatic eruptions. That would create a young appearance through steady overturn, the way a conveyor belt replaces the top layer. Convection depends on layer thickness, temperature gradients, and viscosity, all of which depend on composition and grain structure. New Horizons provides patterns consistent with cellular overturn, but not definitive proof, and that ambiguity is part of the scientific texture. The strength of the claim is that renewal is happening, not exactly how. This distinction matters because it separates observation from mechanism. The observation is a surface that looks young, smooth, and patterned. The mechanism could be convection, glacial flow, sublimation-driven resurfacing, or some combination. Pluto may be using multiple tools at once, each one subtle, each one slow, each one sensitive to small shifts in temperature and albedo. The mystery is not whether Pluto changes, but how it budgets energy to do it. The chapter's tension comes from the mismatch between environment and activity. Pluto receives about 1/1500th of Earth's sunlight, yet it shows glaciers and atmospheric layers. The world is small, yet it holds complex cycles and possible internal liquidity. That combination forces a recalibration of what frozen means. It also forces a recalibration of what edge means, because Pluto is not at the end, and the Kuiper Belt is not a simple graveyard. In the visuals, the spacecraft's trajectory line sweeps past Pluto in a single, clean arc. There is no braking, no orbit insertion, no second chance. The encounter is a high-speed glance, and that makes the detail feel even more precious. Instruments scan in narrow windows, and the spacecraft must choose what to look at and when, because time is geometry. Every image is a slice of time, and every slice suggests processes that outlast the mission. A brief flyby becomes a long argument with our assumptions. Pluto sits near 39 AU, inside the Kuiper Belt's broader domain. The classical belt spans roughly the low 40s to near 50 AU, and resonant and scattered populations extend farther. Pluto is in resonance with Neptune, a stable gravitational rhythm that shapes its orbit. That dynamical context matters, because it tells us Pluto is not an oddball wandering alone. It is one member of a structured population, sculpted by planetary migration early in solar system history, when Neptune's movement rearranged small bodies like stones in a riverbed. Pluto is a milestone on the outward journey, not a boundary marker. Even New Horizons after Pluto still travels within the Sun's near neighbourhood by the documentary's scale standard. The handheld map feels finished here, yet the real architecture keeps going. The Kuiper Belt is wide, and beyond it the distance to the Oort Cloud becomes a different kind of number. Pluto is dramatic, but it is not the final act, and the camera's sense of completion is a human illusion. This matters for the Kuiper Belt as a scientific object, not just as a distance label. Pluto shows that Kuiper Belt worlds can be differentiated, layered, and active. Differentiation means separation by density, with rock sinking and ice rising during early heating. Layering means that composition and temperature can vary with depth, enabling different mechanical behaviors. Activity means that surfaces can be renewed, atmospheres can cycle, and chemistry can proceed. The belt is not only a museum of untouched relics, even if some bodies are pristine. It is a population with multiple thermal histories and multiple compositions. Some objects may have formed with more rock, producing more radiogenic heat. Some may have retained more volatiles, enabling seasonal transport. Some may have experienced impacts that reset surfaces, or created basins that trap ices. Pluto is one data point, but it widens the plausible range for thousands of unseen ones. It also raises a sharper interpretive challenge. How many quiet worlds are being misread because we only see their averaged light? The implication is not that every Kuiper Belt object is alive with geology. Many will be small, inert, and cratered, preserving ancient surfaces like cold stone. The implication is that the parameter space is wider than assumed. Size, composition, porosity, and orbital history can produce very different outcomes. A single close-up world expands the range of what we must consider when we interpret faint light curves and sparse spectra, and it makes humility part of the method. Pluto also changes how we interpret distant observations. When a telescope sees brightness changes or unusual colours, Pluto reminds us those signals can reflect active transport rather than static stains. When we see spectral signatures of nitrogen or methane, Pluto shows they can be mobile and seasonal. When we model crater retention, Pluto shows resurfacing can erase the record. The Kuiper Belt becomes less like a static background, and more like a set of ongoing experiments, running slowly in the dark. At the same time, the scale theme must stay in frame, because it is the documentary's quiet antagonist. Pluto's orbit is far in human terms, yet it is still close on the Sun's full scale. If the Kuiper Belt feels like the edge, It is because it is the farthest region we have seen well. The Oort Cloud comparison will later reveal how small this frontier really is. Pluto is a dramatic close-up, but it's still deep inside the first false ending, and the real boundary remains beyond our emotional arithmetic. New Horizons carries that tension forward as it leaves Pluto behind. The spacecraft's path continues outward, and the data stream turns into a long-distance conversation that takes hours to cross the void. Engineers and scientists wait for packets, reconstructing a world line by line and watching a signal that is already history when it arrives. The mission becomes a bridge between two Kuiper Belt extremes. Pluto represents complexity, differentiation, and active volatile geology. The next target will represent something closer to untouched origin. Arrokoth enters as the transition object, chosen to sample a different kind of Kuiper Belt history. It is small, cold, and shaped like a gentle merger, suggesting low-velocity accretion in the early disk. It lacks Pluto's obvious atmosphere and large-scale resurfacing, and that absence is itself a clue. It offers a counterpoint that helps separate what is common from what is exceptional. One spacecraft captures both ends of the belt story, and it forces a question that is as much philosophical as scientific. Is complexity the rule, or the rare exception we happen to visit? The chapter closes by tightening the central question again. Because Pluto does not resolve the mystery, it deepens it. If Pluto can maintain cycles under weak sunlight, what other worlds are quietly changing beyond the range of our best telescopes? If a dwarf planet can plausibly hide an ocean, what does that imply for other large KBOs with similar compositions? If the Kuiper Belt is not a museum, then the unseen outskirts may be even less predictable. And if Pluto is only 39 AU out, the real boundary of the solar system remains far beyond our intuition. Next, New Horizons meets Arrokoth, and the narrative pivots from active world to pristine relic. The contrast will sharpen what the Kuiper Belt preserves and what it transforms. It will also keep the scale argument honest, because even Arrokoth is still near the inner rim. After that, the documentary can widen from close-up geology to the terrifying distance gap. The Kuiper Belt will start to look small, and the Oort Cloud will begin to loom. New Horizons leaves Pluto behind, and the Kuiper Belt becomes quiet again. The bright, backlit crescent of Pluto shrinks into a pale point, and the spacecraft's radio signal steadies into the long, thin cadence of cruise. There is no braking burn, no circularization, no second chance. Flyby energy is a one-way commitment written into the trajectory. In that outward drift, the central question sharpens in a new way. How do we compare what we can image in crisp pixels to what we can only infer from statistics and faint light? Pluto proved that cold worlds can be active, layered, and surprisingly young. Its nitrogen glaciers, its haze layers, and its fractured water-ice bedrock rewrote the old assumption that distance equals dormancy. Even its atmosphere, thin, seasonal, and easily lost, showed that volatile cycles can persist far from the sun. The next target is chosen for the opposite reason, because it looks older than history. Arrokoth is small, dim, and distant, sitting in the cold classical Kuiper Belt like a fossil that never left the sediment. Even its discovery name, 2014 MU69, felt like a catalogue entry for something meant to stay anonymous. Arrokoth's orbit is low inclination and low eccentricity, and that geometry matters. It moves in a relatively flat path, close to the plane where the planets formed, rather than tilting high above and below it. Its distance from the Sun changes only modestly across its year, which in the Kuiper Belt lasts centuries. Those are not just orbital trivia points, because orbits are the memory of past encounters. A body that has been scattered hard by Neptune tends to carry the scar in its eccentricity and tilt. In dynamical language, the orbit behaves like a long-lived diagnostic. Stable patterns imply a gentle history, while wild angles imply past violence. The cold classical region is a kind of protected neighbourhood in dynamical terms. Objects there tend to keep flatter, calmer orbits, implying limited disturbance since formation. They are not immune to everything, because gravity never truly stops working, yet they are less processed by Neptune's scattering. When we say primordial here, we mean dynamical survival across 4.5 billion years. It is a cautious word because nothing is perfectly preserved, but it is still the closest thing we have. The remarkable point is not that these bodies avoided change entirely, but that they avoided the kinds of encounters that erase identity. That idea has a history of its own, built from decades of orbital surveys and computer integrations. In the early 20th century, astronomers argued about a possible reservoir beyond Neptune, and later work by Gerard Kuiper helped popularize the concept of a distant belt. The first Kuiper Belt object after Pluto and Charon was not found until 1992, when improved detectors finally made the faint dots countable. Since then, the cold classical population has stood out in the data as a distinct clan, dynamically colder and often redder than many of its neighbours. The pattern emerged slowly as telescopes widened their surveys and as software learned to connect nights of motion into a single orbit. Arrokoth is not a planet, and it does not pretend to be one. It is a planetesimal, a building block that never graduated into something larger. That makes it valuable, because it preserves an early stage we usually lose. In the inner solar system, the same stage was erased by impacts and by growth. Rocks became boulders, boulders became protoplanets, and protoplanets became worlds that recycled their surfaces. Out here, the construction site went quiet before the scaffolding was cleared away, so the scaffolding remains. New Horizons approaches Arrokoth at a closing speed of about 14 kilometers per second, fast enough that the encounter is over in hours. On the navigation screens, the target begins as a star-like speck, then becomes an unresolved blur, and then, suddenly, two lobes. The flyby reveals a contact binary, two bodies joined like a snowman resting in deep freeze. The shape is not a gimmick, it is a physical record of assembly. The silhouette is so distinctive that it feels almost designed, and that is exactly why it matters. In the raw frames, the object seems to rotate out of the darkness, lit from one side by a distant sun. A violent collision would have shattered or heavily deformed such a fragile body. At Kuiper Belt temperatures, water ice behaves like rock, yet porous mixtures of ice and dust can still be mechanically weak. The intact lobes imply a gentle merger at very low relative speed, likely comparable to walking pace rather than orbital speed. That conclusion is not based on aesthetics, but on impact physics and on what fragile aggregates can survive. If the collision had been fast, the neck would be a rubble scar, not a smooth seam. The lobes would also show widespread fracturing, and the overall outline would look blunted rather than preserved. That seam, the narrow waist where the lobes meet, becomes a kind of timestamp. In high-resolution images, it looks brighter in places, as if fine material slid downhill and pooled in the gravitational low. The lighting geometry exaggerates the relief, and the terminator line crawls across the surface like a slow tide. Shadows stretch long because the sun is far away, and the illumination is almost purely directional. Every ridge and depression reads as a sharp contrast, as if the object were carved from charcoal and chalk. The neck is also a trap for loose grains, because the local slopes and gravity guide particles toward the lowest potential. This conclusion points backward to how planetesimals formed in the first place. One older picture imagined incremental growth through frequent collisions and sticking, a slow ladder built from countless impacts. Another picture emphasizes gravitational collapse in a dense pebble cloud, followed by soft mergers and binary formation. Arrokoth's form supports the low-velocity end of that spectrum. It suggests that at least some planetesimals were born in environments gentle enough to preserve delicate geometry. The question becomes unavoidable. If this is what gentle assembly looks like, how common was gentleness in the early disk? The incremental growth story was never simple, because sticking is hard when collision speeds rise. Small grains can cling through electrostatic forces, but as bodies grow, impacts become energetic and bouncing becomes common. Laboratory experiments and numerical models showed barriers: fragmentation, erosion, and the tendency for objects to drift inward before they can grow. Those difficulties pushed theorists to look for collective effects, where the disk itself helps concentrate solids. The modern view often blends mechanisms, but Arrokoth highlights the quietest pathway. It hints that the earlier steps may have been less like a hailstorm and more like a settling fog. In a cold disk, relative speeds can stay small if the environment is dynamically calm. Small solids can concentrate through streaming instabilities, building dense clumps in the gas. The basic idea is subtle but powerful. As pebbles drift through gas, they can self-organize into filaments and knots, because drag forces couple their motion. Once a clump becomes self-gravitating, it collapses into a swarm of bound pieces. Those pieces can settle into binaries and contact binaries without catastrophic impacts. In practical terms, the disk can do the gathering for you, turning many small drifters into one coherent pile. Gravitational collapse is not a single clean event, like a rock falling straight down. It is a chaotic settling, where many fragments exchange energy, collide softly, and sometimes pair off. In that swarm, angular momentum matters, because it decides whether the final outcome is one body, two bodies, or a small system. Binaries can form naturally when two pieces become bound, and the rest of the swarm carries away energy. Over time, gentle interactions can tighten the orbit, turning a wide pair into a close pair. The result is a kind of natural sorting. Some pieces escape, some remain, and a few lock into stable companionship. A contact binary is a special outcome of that gentle regime. Two components form near each other, orbit slowly and lose energy through interactions with surrounding debris. Even weak tides can dissipate energy when the bodies are close, and repeated micro-impacts can act like a brake. Over time, the orbit shrinks and the bodies touch and stick. The neck region becomes a seam that preserves the moment of contact. It is a frozen handshake from the earlier solar system. The seam is also a reminder that collision does not always mean destruction, especially when the relative speed is barely more than a drift. The orientation of the lobes adds another clue, because Arrokoth rotates in a way that suggests a coherent history. Its spin is not wildly chaotic, and the lobes appear aligned rather than randomly smashed together. That alignment is easier to explain with a gentle inspiral than with a high-speed collision. In a calm disk, two components can share the same local environment, and their relative motion stays slow. The result is an object that looks assembled rather than wrecked. The geometry feels intentional, yet it is simply the outcome of physics operating at low energy. This is the contrast with the inner solar system, where collision speeds were higher. Closer to the Sun, orbital velocities are larger, and gravitational stirring is stronger. The growing protoplanets acted like agitators, pumping eccentricities and inclinations and turning encounters into impacts. Impacts there tend to fragment and melt, not softly merge and preserve shapes. Arrokoth becomes an argument that formation pathways depended on location. It is a reminder that one solar system contained many different construction zones. If the inner region was a furnace and a demolition site, the outer region could be a cold workshop where delicate assemblies survived. The surface adds a second line of evidence because it is uniformly reddish. That colour is not paint, it is chemistry and radiation history written into the uppermost microns. Sunlight, ultraviolet photons and cosmic rays break apart simple ices, even in deep cold. The fragments recombine into complex organics that darken and redden the surface. The process is slow, but it is relentless, and time is the one resource the Kuiper Belt has in abundance. The topmost layer can be altered while the bulk remains unchanged, like a weathered rind on a frozen interior. In visible images, the red tone is subtle but unmistakable, like dried rust under a thin veil of soot. In spectral data, it becomes a slope, reflectance rising toward longer wavelengths, consistent with complex carbon-rich residues. The surface is also dark overall, meaning it reflects only a small fraction of sunlight. That darkness matters for temperature, because low albedo surfaces absorb more energy, though at this distance the sun is still a weak heater. The object sits only a few tens of degrees above absolute zero, yet chemistry still proceeds. Even a tiny trickle of energy delivered steadily for eons can rearrange molecules and build complexity. These residues are often called tholins, a broad label for complex organic solids. They form when methane, nitrogen compounds, and other carbon-bearing molecules are processed by radiation. The result is a reddish spectral slope that telescopes see across many Kuiper Belt objects. Arrokoth shows the same signature up close, without the confusion of distance. It is the difference between guessing a landscape from a blurry photograph and standing on the ridge. Close up, the redness becomes a physical surface, not just a number in a catalogue. The term tholins carries its own history, rooted in laboratory experiments that tried to mimic planetary atmospheres and icy surfaces. Researchers exposed simple gases and ices to ultraviolet light and energetic particles, then watched as sticky, tar-like residues accumulated. The products were not a single molecule but a complex mixture, often containing aromatic rings and nitrogen-bearing compounds. In plain language, radiation turns simple ingredients into complicated ones. The Kuiper Belt, despite its cold, is a long-running chemical reactor. The experiments were a reminder that chemistry does not need life to become intricate. It needs only ingredients and persistence. The key idea is that organic chemistry does not require warmth, it requires time. At tens of AU, the photon flux is low, yet it never stops, and cosmic rays arrive from beyond the solar system. Over millions of years, slow processing still builds complex molecules layer by layer. The Kuiper Belt becomes a chemical factory that runs on patience. It asks a quiet question: how much complexity can accumulate without liquid water or sunlight strong enough to melt ice? And if complex organics can form on these frozen surfaces, what does that imply about chemistry in even darker interstellar environments? Arrokoth's surface also looks lightly cratered at the scales New Horizons could resolve. That suggests a low impact rate in the cold classical region, consistent with its dynamical calm. Fewer impacts mean fewer resets, and fewer resets mean older surfaces remain legible. The object becomes a time capsule, not because it is untouched, but because it is lightly rewritten. Even a small number of impacts can garden the surface, yet the overall record still feels sparse. In the images, the terrain reads as gentle undulations rather than a battlefield of overlapping scars. Crater counting is a blunt tool at these distances, because resolution limits what we can see. A small crater can vanish into a pixel, and a shallow depression can hide in low-angle lighting. Even so, the relative lack of obvious large craters is informative, especially when compared to more heavily battered bodies. It implies that the cold, classical belt has been a quieter place for a very long time. Quiet does not mean empty, but it means less violent. The absence becomes a kind of presence, evidence that the environment did not constantly erase what came before. This is where the chapter turns from one object to the structure around it. Arrokoth is a point sample of a population we mostly know as faint dots. The cold classical belt is only one component of the Kuiper Belt's architecture. The belt also includes resonant groups and the scattered disk, each with different histories. In orbital space, those groups form patterns that look almost like fingerprints, each one shaped by Neptune's gravity. When we plot them, the solar system stops looking like a simple diagram and starts looking like a record of movement. Resonant objects are locked into rhythmic relationships with Neptune, orbiting in ratios like 3.2 or 2.1. Pluto itself is the famous example, protected from close encounters by resonance choreography. These resonances are not accidents, because they can capture objects during planetary migration. If Neptune moved outward early in solar system history, its resonances would have swept through the disk like a comb. Some objects would be trapped, others scattered, and a few would remain in the calm zone. The resonances act like moving traps, and their very existence implies that the giant planets did not always sit where they are now. Mass is the hidden variable in that architecture, and it is hard to measure directly. We see the largest objects because they reflect enough light to detect, and even then the light is faint. We infer sizes from brightness, then guess albedo, then revise with better constraints from stellar occultations or thermal measurements. The smallest bodies dominate the number count, and they may dominate the collisional environment. The problem is that they are effectively invisible at interplanetary distances. In a region where most members are unseen, the few we detect can mislead us about the whole. Brightness is a tricky proxy, because a small bright object can mimic a large dark one. Without a direct size measurement, every estimate carries an uncertainty that propagates into population models. Surveys also have biases because they miss objects that move slowly, objects that are too faint, or objects located in crowded star fields. Even with modern telescopes, the Kuiper Belt is a census with missing pages. That incompleteness is why indirect tracers become so valuable. The belt is not just far, it is statistically slippery. Its reality is partly hidden inside our detection limits. If the Kuiper Belt once held much more mass, it could have built larger worlds more efficiently. Many models require early depletion, because the present belt is too sparse to grow Pluto-sized bodies quickly. Depletion could come from Neptune's migration and scattering, or from collisional grinding that turned large bodies into dust. The belt we see today may be the remnant of a much richer disk. In that sense, the Kuiper Belt is not only a place, but a leftover. It is a shoreline after a retreating sea, where what remains hints at what once filled the basin. The idea of early depletion connects to broader stories about the giant planet's evolution. Migration models, developed to explain resonances and orbital distributions, imply that Neptune's path was not fixed. As it moved, it would have destabilized parts of the disk, ejecting material inward and outward. Some of that material could have fed impacts in the inner solar system, while other pieces were thrown toward interstellar space. The calm, cold classical region looks like what remained when the storm passed. In that framing, Arrokoth is not merely distant, it is sheltered, a survivor of a rearrangement that reshaped the entire outer system. New Horizons carries an instrument that can test that idea indirectly. A dust counter does not image worlds, it counts impacts of tiny particles. Each hit produces a signal that can be sorted by amplitude, which relates to particle mass and speed. Over time, the instrument builds a profile of dust density along the spacecraft's path. It is a different kind of seeing, less like a camera, more like listening for raindrops on a roof. The method is almost humble, yet it reaches where telescopes cannot because dust is everywhere and brightness is not required. The instrument, called the Student Dust Counter, is deceptively simple in concept. A thin panel registers the tiny electrical pulse produced when a grain strikes at high speed and vaporizes. The pulse height gives a rough measure of the impactor's mass, while the count rate maps how often grains are encountered. Because the spacecraft's speed through space is known, the data can be translated into a dust flux. It is a way to probe populations too small for telescopes. In visual terms, each impact is a microscopic flash of plasma, brief, invisible to our eyes, yet recorded as a measurable signature. Dust in the outer solar system is produced by collisions among small bodies. When objects collide, they generate fragments that can cascade down to micron and submillimeter sizes. Radiation pressure and the solar wind can push on the smallest grains, while gravity shapes their orbits. Pointing. Robertson drag can slowly spiral some particles inward, although the effect weakens far from the Sun. The dust population is therefore a tracer of unseen small bodies and ongoing collisions. If you cannot count the parent bodies directly, you count the debris they shed. Each grain is a messenger, but it is also a survivor of a harsh environment. Charged particles from the solar wind can alter grain trajectories, especially for the tiniest sizes, and electromagnetic forces can become relevant. Some grains are swept into resonances, while others are expelled or ground down further by additional impacts. The dust cloud is dynamic, not static, and its structure can reflect the structure of the parent populations. In other words, dust is the Kuiper Belt speaking in whispers. The whisper is faint, but it is continuous, and continuity is often more revealing than drama. The surprise is that New Horizons detected more dust than some models predicted. The counts did not fall off as quickly with distance as expected, even as the spacecraft moved beyond Pluto. That result is not a single dramatic spike, it is a persistent elevation. It hints that the source region for dust may be larger, denser, or more extended than assumed. When a quiet instrument keeps disagreeing with expectation, the disagreement becomes a clue. It forces us to ask whether our maps are missing objects, missing processes, or missing an entire faint component of the disk. Some models had predicted that dust density would drop sharply past the main concentration of Kuiper Belt objects. If the belt were sharply bounded, fewer collisions would occur beyond that edge, and fewer grains would be produced. Instead, the dust counter kept hearing impacts, as if the environment remained busier than the map suggested. The effect is subtle in any single day of data, yet persuasive when accumulated over years. It is the power of patient measurement. In a place where change is slow, only long baselines can reveal what is truly steady. There are several interpretations, and each one widens the map. Elevated dust could mean more small Kuiper Belt objects than our surveys imply, especially bodies too faint to detect directly. It could mean the size distribution contains more fragile objects that grind down efficiently when they collide. It could also mean a broader disk that extends beyond the classical belt's apparent edge. The same data can support multiple stories, and that is where inference becomes delicate. The dust counter does not identify the parent body. It only testifies that something is colliding somewhere. An extended Kuiper Belt is not a neat ring beyond 50 AU. It is a hypothesis that low-density populations continue outward, too sparse and too dim for easy detection. Some objects already suggest this, including detached bodies with perihelia beyond Neptune's strong reach. Their orbits look like they were lifted away from the planet's direct control. The dust data adds pressure to take that extension seriously, because dust does not respect our catalogue boundaries. If the belt fades rather than ends, then edge becomes an artifact of our sensitivity. This is where the narrative tension rises, because the Kuiper Belt's boundary becomes less certain. The belt feels measurable, because we can catalogue objects and map resonances, and those maps look authoritative. Dust counts suggest that what we catalogue may be only the brighter crest of a larger distribution. The structure could fade outward gradually, not end cleanly. In the far dark, a gradient is harder to recognise than an edge. The question becomes philosophical as well as scientific. What does it mean to draw a border around something we can barely see? The visuals of this uncertainty are almost paradoxical. On one screen, there are tidy orbital plots, coloured families, and labelled resonances. On another, there is a simple graph of dust impacts versus distance, and the curve refuses to drop as expected. One is geometry, the other is statistics, and both are real. The Kuiper Belt becomes a place where different kinds of evidence overlap imperfectly. That overlap is where new understanding usually begins. It's also where mystery lives, because the simplest story is no longer sufficient. Beyond the cold classical belt, the scattered disk provides a known pathway outward. Scattered objects have high eccentricities and perihelia still influenced by Neptune, meaning they come close enough to be tugged. They are not stable in the same way, and their orbits can evolve chaotically over long timescales. They represent a bridge from orderly resonances to stretched transitional trajectories. In a sense, they are the Kuiper Belt's emigrants. Their orbits are elongated signatures of repeated negotiation with a giant planet's gravity. A scattered object's orbit often looks like a long ellipse, with a distant aphelion and a perihelion that grazes Neptune's realm. Each close approach can change the orbit, sometimes subtly, sometimes dramatically. Over millions of years, a sequence of encounters can walk an object outward, inward, or out of the solar system entirely. This is gravitational diffusion in action, a random walk driven by planetary mass. The scattered disk is therefore both a population and a process. It is also a reminder that stability is not binary, because bound can still mean slowly changing. The scattered disk also connects to the idea of detachment and long-term lifting of perihelia. Interactions with Neptune can scatter an object outward, then resonances and secular effects can modify its orbit. A resonance can temporarily protect an object while also pumping its eccentricity or inclination. Over even longer times, passing stars and galactic tides become relevant, slowly reshaping the farthest orbits. The solar system's boundary begins to feel porous rather than fenced. At great distances, the sun's grip weakens enough that the galaxy becomes a background hand on the scale. The notion of passing stars influencing distant orbits is not speculative hand-waving, because the sun formed in a stellar neighbourhood. In the early cluster environment, close stellar passages were more likely than they are today. Even now, over billions of years, the sun drifts through the galaxy and encounters other stars at safe but influential distances. At thousands of AU, safe is relative, because gravity has a long reach. The farthest objects live in a regime where the galaxy becomes a participant. The same gravity that keeps planets in place can, at the margins, be gently undone by repeated outside nudges. This bridge matters because it points toward the next reservoir in the story. The Oort Cloud is not a continuation of the Kuiper Belt's disk. It is a different geometry. It is inferred as a distant, roughly spherical shell of icy bodies surrounding the solar system. The scattered disk is one of the routes by which objects can be fed outward into that shell. The disk flattens into a sphere, not by magic, but by countless weak tugs over time. The transformation is slow, but it is cumulative, and cumulative effects are the outer solar system's specialty. The Oort Cloud itself carries a historical signature in its name. Jan Oort proposed it in 1950 to explain the distribution of long-period comet orbits, which did not cluster in the plane of the planets. If comets came from a disk alone, their approach directions would be biased toward that plane. Instead, they arrived from all over the sky, as if falling inward from a distant shell. Oort's inference was bold, because the reservoir was invisible, yet the comets made it necessary. It was a triumph of orbital reasoning, the kind of astronomy that turns trajectories into geography. Comets are the messengers that make this inference possible. Short-period comets, with periods under about 200 years, are tied to the Kuiper Belt and scattered disk pathways. They're captured into smaller orbits through repeated interactions with the giant planets. Their composition and activity carry signatures of formation in cold regions. They are also dynamic objects, constantly reshaped by sunlight when they come close. Each return trip is both a measurement and an erosion, a sampling that also changes the sample. A short-period comet's orbit is a history of gravitational encounters. Jupiter and Saturn can reshape it quickly, while Neptune can supply it from the outskirts. Many become Jupiter family comets, with orbits controlled by Jupiter's gravity and with inclinations typically modest. Their existence implies a continuing source of icy bodies beyond Neptune. Without that source, the population would fade, because comets do not survive indefinitely. The fact that we still see them is evidence that the outer reservoirs are not just historical, they are active suppliers even now. The capture process is a kind of celestial pinball. A body approaches a giant planet, steals or loses orbital energy, and leaves on a new path. Repeated encounters can shrink the orbit until the comet becomes a regular visitor to the inner solar system. But the same process can also eject a comet, flinging it outward on a hyperbolic escape. Every comet we see is therefore a survivor of a chaotic selection. The fact that any arrive at all tells us the reservoir is large. It also suggests that the solar system is not closed, because ejection is as much a part of the story as capture. Comets also connect chemistry to dynamics in a way Arrokoth cannot. When a comet approaches the Sun, ices sublimate and release trapped gases and dust. Spectra reveal water, carbon monoxide, carbon dioxide, and complex organics, sometimes including molecules with nitrogen and sulfur. Each detection is a clue about what was stored in the outer disk. The coma becomes a temporary atmosphere, and the tail becomes a visible vector pointing away from the Sun. For a brief time, a small nucleus writes its composition across the sky in gas and dust. Visually, a comet is a transformation. A dark nucleus, often only a few kilometers across, suddenly grows a glowing envelope that can span tens of thousands of kilometers. Jets punch through the surface, driven by localized heating and volatile pockets. Dust grains scatter sunlight into a pale fan, while ionized gas streams into a narrow bluish line shaped by the solar wind. The spectacle is physics made visible: sublimation, radiation pressure, and plasma interaction in motion. It is also a reminder that the outer solar system is not only remote, because it can announce itself dramatically when a fragment wanders inward. Yet comets are also altered by their journeys, and that complicates the evidence. Repeated heating can drive off volatiles and change surface layers, building crusts that insulate what lies beneath. Jets can reshape the nucleus, carving pits and cliffs, and fragmentation can erase original structure. Some comets split into multiple pieces, turning a single object into a transient swarm. Arrokoth, by contrast, has not been repeatedly baked, and that makes it a cleaner artifact. The difference is like comparing a preserved fossil to a living animal that has endured injury, repair, and adaptation. This difference is crucial for interpretation. A comet's surface is a working surface, constantly evolving, while Arrokoth's surface is closer to a long-term exposure experiment. Both are valuable, but they answer different questions. Comets tell us what becomes active when warmed, and Arrokoth tells us what remains when left cold. Together they bracket the range of outer solar system behavior. The contrast helps separate original composition from later processing. It also raises a subtle thought: how much of what we call primitive is truly original, and how much is simply old? So the chapter holds two kinds of evidence side by side. Arrokoth is quiet evidence, a preserved shape and surface chemistry in a stable orbit. Dust counts are noisy evidence, a statistical signal of unseen populations spread across vast distances. Comets are travelling evidence, altered but still informative, linking the belt to the inner system. Each one is incomplete alone, yet together they form a chain of inference. The chain is not made of certainty, but it is made of consistent hints that point in the same outward direction. The Kuiper Belt now looks less like an edge and more like a gradient. The cold classical region preserves gentle formation, while resonant and scattered populations record migration and disruption. Dust hints that the gradient may extend farther than our catalogues, fading into regions we have barely sampled. The map begins to blur at the margins, not because the structure is absent, but because our measurements thin out. In the outer solar system, ignorance often looks like emptiness, and emptiness can be a mirage created by distance, darkness, and the limits of our instruments. This is the moment to restate the documentary's scale hook in practical terms. On a handheld map, Arrokoth feels like the farthest reachable shoreline, a last landmark before the blank. In physical scale, it is still close to the Sun compared to what comes next. The Kuiper Belt is wide in AU, yet it is thin compared to the distances implied by long-period comets. Even the word far changes meaning when the unit is an astronomical unit. The camera can show a world at 40 or 50 AU, Yet the next reservoir begins where even numbers start to feel abstract. New Horizons itself embodies that scale, because its signals take hours to reach Earth. Commands go out, confirmations come back, and the spacecraft continues regardless, moving through a region where sunlight is weak and radioisotope power is precious. The images it sends are not live views, but delayed postcards from a receding frontier. That delay adds to the mood because discovery arrives after the fact. We learn what happened when it is already gone. Even the act of looking becomes a kind of archaeology, because the spacecraft has already moved on by the time we understand what it saw. Arrokoth also reframes what we mean by origins. It suggests that some planetesimals formed by collapse and gentle mergers, not by constant high-speed impacts. That changes how we imagine the first steps toward planets, because it shifts emphasis from individual collisions to collective behavior in a disk. It also implies that the outer disk could preserve fragile structures for billions of years. If such structures survived here, what else survived? Unseen, in colder and darker places. The object's very existence is an argument that early solar system conditions were not uniformly violent, and that calm had a role in building worlds. The dust clue then pushes the story outward again, because it suggests more material beyond the neat categories. If the belt is more extended, then the transition to the scattered disk may be broader. If the scattered disk is broader, then the feeding of distant reservoirs may be more efficient. Each extension makes the solar system's footprint larger than our intuition. The boundary becomes a zone, and the zone becomes a continuum. The picture that emerges is not a set of rings, but a fading distribution shaped by gravity, time, and chance. We end the chapter by tightening the evidence trail that leads outward. Kuiper Belt objects are measurable worlds, even when they are faint and far, and Arrokoth proves that close-up measurements can overturn assumptions. Dust is measurable too, even when the sources are invisible, and its persistent counts challenge simple edges. Comets are the final link because they arrive as physical samples of distant storage, carrying gases and grains into our instruments. The trail is not direct, but it is coherent. It is a scientific kind of storytelling, where each clue is partial, yet each clue narrows what the next chapter can be. The next step is where measurement gives way to inference. Long-period comets arrive from directions that do not align with a flat disk, and their inclinations scatter across the sky like thrown darts. Their orbits suggest a distant, roughly spherical source, because only a sphere can feed comets from all directions. That source is the Oort Cloud, a reservoir we have never seen yet cannot ignore. The evidence is indirect, but the pattern is stubborn. If the Kuiper Belt is a frontier we can still chart, the Oort Cloud is a frontier we can only deduce. From Arrokoth's quiet merger seam to a dust counter's unexpected tally, the Kuiper Belt stops feeling like a boundary. It becomes a doorway, and the doorway opens onto darkness measured in thousands of AU. The story moves from the farthest close-up world to an unseen shell inferred by visitors from the cosmic dark. The question lingers as the spacecraft continues outward. How much of our solar system is still present, simply beyond our ability to see? Comets are the solar system's courier service, carrying outer ice and dust inward as if they were sealed parcels from a colder era. They turn distant reservoirs into measurable events, spectra, tails, sudden brightenings, then vanish again into darkness, leaving only orbital elements and fading memories. For astronomers, that brief visibility window is priceless, because it converts unreachable distance into data you can plot and compare. In this chapter, we follow that pipeline from Kuiper Belt chaos to whispers of an unseen planet, and we treat every orbit as a clue. A comet is not just a pretty streak in the sky, even when it looks like a brushstroke across twilight. It is a moving sample of ancient material, preserved at low temperatures and delivered briefly into sunlight. When it warms, it becomes a natural laboratory. Ices sublimate, dust lifts, and chemistry that was frozen for eons suddenly runs in real time. We start with a practical split that organizes the whole mystery, and it begins with time. Short-period comets orbit the Sun in less than about 200 years, returning often enough that astronomers can watch them age. Long-period comets take longer than 200 years, often thousands or millions before returning, if they return at all. That cutoff is conventional rather than sacred, but it cleanly separates two dynamical histories that leave different fingerprints. That period difference is not just bookkeeping, it is geography in disguise. because orbital period tracks distance through Kepler's laws. Short periods imply repeated visits and repeated planetary encounters, which steadily remodel the orbit and the nucleus. Long periods imply a source so distant that one orbit becomes a lifetime, and a single pass can be the only chapter we ever read. The same math that predicts a return date also hints at where the comet spent almost all of its existence. On screen, the distinction is easy to see if we draw the solar system as a set of nested tracks. Short-period comets mostly arrive along the planetary plane because their source is disk-like and dynamically linked to the ecliptic. Long-period comets arrive from all directions, hinting at a roughly spherical source that surrounds the Sun like a halo. In a rotating 3D view, the short-period paths look like flattened loops, while the long-period paths stab inward like needles from every angle. Jupiter family comets are the most familiar short-period group, and they anchor the story because we can observe them repeatedly. Their periods are typically under about 20 years, and Jupiter dominates their orbital shaping through close approaches and repeated perturbations. They are best explained as Kuiper Belt descendants, filtered through the scattered disk, then handed inward by the giant planets. Even their name is a dynamical label, because it points to the planet that most strongly controls their current motion. The key idea is capture through repeated gravitational nudges rather than a single dramatic shove. A small body drifts inward from beyond Neptune, then meets the giant planets in a sequence of encounters that change its orbital energy. Each encounter can be tiny, but the changes accumulate until the orbit is no longer a distant ellipse. Over time, the comet's path becomes less like a long, lonely swing, and more like a loop that repeatedly crosses the inner system. Orbital mechanics can sound abstract, so we keep it tactile and visual, like a slow game played on a curved table. Gravity is not one shove, it is a sequence of tugs that depend on timing, geometry, and speed. Over millions of years, tiny changes add up like compound interest, and the ledger is written in semi-major axis, eccentricity, and inclination. Those elements are not just numbers in a catalogue, because they encode a history of near misses and resonant rhythms. In the simplest terms, orbital energy tells us how tightly a comet is bound to the Sun. A small change in velocity near a planet can shift that binding energy, nudging the comet toward a shorter period or pushing it outward again. The same encounter can also rotate the orbit in space, changing where the comet will cross the planetary region next time. In practice, the most important changes often happen near perihelion, where the comet moves fastest and small impulses matter more. Neptune is the first major sculptor in this pipeline, because it sits at the gateway between the Kuiper Belt region and the deeper outer darkness. Objects in the scattered disk approach Neptune near perihelion, then get scattered again by a close pass that can be gentle or violent. The orbit can stretch outward, shrink inward, or tilt away from the original plane, and the outcome depends on a few minutes of celestial geometry. In a simulation, a single close approach can kink a trajectory so sharply that the before and after orbits barely look related. The scattered disk itself is a clue that this process has been running for a long time. It is populated by bodies whose orbits are elongated and dynamically excited, as if they were repeatedly stirred and tossed. When we map their paths, we see a record of Neptune's long reach, written across many different inclinations and perihelion distances. The population is also a reminder that the outer solar system is not quiet, because even distant objects can be rearranged by slow, persistent interactions. Some objects do not scatter randomly, because resonances organize the chaos and impose rhythm on what would otherwise be a blur. A resonance is a repeating relationship between orbital periods, like 2-1 or 3-2, that causes encounters to recur in similar configurations. In resonance, a body meets Neptune in the same orbital geometry again and again, which can stabilize or destabilize the orbit depending on the details. The repetition is the key, because repeated timing can either prevent close approaches or set them up with eerie reliability. That repetition can protect an object from close encounters, as Pluto's 3-2 resonance demonstrates with almost theatrical reliability. Pluto crosses Neptune's orbital distance, yet the resonance keeps their closest approaches safely separated in time and space. The same principle can also pump eccentricity or inclination, slowly reshaping an orbit until it becomes a candidate for the comet pipeline. Resonances are not merely mathematical curiosities, because they act like traffic rules that decide which lanes stay safe and which lanes drift toward danger. Resonances become both shelters and launch ramps, and the difference is subtle but crucial. A resonance can lock an object into a pattern that avoids Neptune, preserving it for billions of years in a stable niche, or it can gradually increase the orbit's eccentricity, lowering perihelion until the object begins to graze the realm where scattering becomes likely. In that second case, the resonance is not a refuge, it is a slow escalator, quietly delivering a body toward the planetary gate. Resonant pumping matters because it can inject bodies into cometary pathways without a single catastrophic event. A modest change in perihelion can move an object from stable storage to planetary reach, and the transition can happen quietly. Once it crosses that threshold, the inner system does the rest, and the object becomes a traveller rather than a resident. The pipeline is therefore partly deterministic and partly chaotic, because resonances set the stage and close encounters improvise the details. When a scattered object's perihelion drops toward the giant planets, Jupiter and Saturn become the next gatekeepers, and their influence is unmistakable. Their larger masses produce stronger deflections and faster orbital evolution, because the gravitational impulse during a close pass scales with mass and proximity. A few close encounters can transform a distant ellipse into a short-period loop, and the comet's future becomes a story of repeated returns. In the inner system, the timescales compress, and a million-year drift can become a century-scale cycle. Here the visuals can slow down, showing a comet's path as a glowing thread that kinks and tightens after each planetary flyby. The changes are not random in the everyday sense, but they are sensitive to initial conditions like weather patterns. A slight difference in approach distance can decide whether a comet becomes bound more tightly, gets ejected, or is diverted into a new inclination. That sensitivity is why two comets that look similar in a catalogue can diverge into completely different fates. This is why Jupiter family comets are not just visitors, they're a population with a supply chain that must be continuously replenished. Comets fade, fragment, and lose volatiles because sunlight drives sublimation and jets that carry mass away. The continued presence of Jupiter family comets implies a continuing reservoir beyond Neptune, feeding a pipeline that never fully shuts off. If the source dried up, the inner system would gradually lose these familiar repeat performers. The fading is not only about losing ice, but also about changing surfaces. As volatiles escape, dust can accumulate into an insulating mantle that suppresses further activity, making the comet appear dormant. Some of these objects may survive as dark, asteroid-like bodies on cometary orbits, reminding us that classification can be a matter of activity, not origin. The nucleus can also spin up from asymmetric jets, sometimes enough to crack, shed chunks, and briefly brighten before it dims again. Historically, this short-period story emerged slowly, because early astronomers could not see the distant source. Edmund Halley's famous prediction in the 18th century showed that at least some comets return on regular schedules, which was a radical shift in understanding. Later, as celestial mechanics matured, the idea of planetary control over comet orbits became a natural extension of Newton's gravity. By the 19th century, astronomers were already using perturbations as evidence, treating comets as test particles that reveal the hidden structure of the system. Long-period comets tell a different story, and they raise the stakes because their orbits reach far beyond the planets. Their paths are nearly parabolic when first observed, meaning they arrive with extremely low binding energy relative to the Sun. Many appear only once, then leave on altered trajectories, and some may never return. In the sky they can look majestic and slow, yet dynamically they are sprinting through the only warm region they will ever touch. A near parabolic orbit is a sign that the comet is barely held, as if the solar system has only a weak grip on it. In orbital terms, the semi-major axis is enormous, and the comet spends almost all its time far from the Sun. We meet it only during a brief sprint through the inner system, when sunlight turns frozen volatiles into visible gas. That gas, often water, carbon monoxide, carbon dioxide, and more complex fragments, glows because sunlight excites it, letting spectroscopy read composition at a distance. The classic inference is the Oort Cloud, a distant shell of icy bodies proposed to explain these arrivals. A shell explains why long-period comets arrive from all directions, not just near the ecliptic, because the source would be roughly isotropic. It also explains why their energies cluster near the escape boundary, as if they are drawn from a reservoir at the edge of the Sun's control. The idea also fits a formation narrative, where early giant planets scattering flung icy bodies outward and the galaxy helped store them. The Oort Cloud idea has a historical weight of its own, because it was built from statistics rather than direct images. Jan Oort analysed the distribution of comet energies in the mid-20th century and noticed a pile-up near very weak binding. The simplest explanation was a vast population of distant bodies parked so far away that small perturbations could send them inward. It was an inference with a philosopher's elegance, an unseen structure revealed by the pattern of rare arrivals. But the Oort Cloud is not the only sculptor of long-period arrivals, because even a shell needs a trigger. At great distances, the Sun's gravity is weak enough that other forces can matter, and the outer solar system becomes sensitive to its environment. The comet pipeline at this scale is not only planetary but galactic. The same solar system that feels self-contained near Earth becomes porous at tens of thousands of AU. Passing stars provide one set of triggers, and the mechanism is surprisingly efficient. A star does not need to come close to the planets to disturb an orbit at tens of thousands of AU, because the comet's binding is so slight. A distant flyby can still change a comet's perihelion enough to send it inward, turning a quiet orbit into a new trajectory. The effect is partly geometry and partly timing, because the direction of the stellar passage decides which orbits are nudged toward the Sun. In a visualization, a star's passage looks like a slow, distant sweep that subtly reorients a cloud of faint points. The comets do not scatter like billiard balls because the encounter is long and gentle compared to planetary flybys. Yet the cumulative effect can be decisive, because it changes angular momentum and shifts where the orbit intersects the inner system. The disturbance is like a tide in a harbour, subtle at any moment, but capable of moving everything given enough time. The galactic tide provides another slow trigger, acting continuously rather than as a rare event. The Milky Way's gravitational field pulls differently on the near and far sides of the solar system, producing a differential force across the Oort Cloud. Over long times, that differential pull can torque distant orbits, raising or lowering perihelia in a slow, almost breathing cycle. The tide is weak compared to the Sun, but the Oort Cloud sits in a regime where weak is enough. These effects are gentle, but the outer system is a patience machine, and patience is a form of power. Weak forces become decisive when they act for millions of years, because the comet's orbit is so large and so loosely bound. The result is a steady trickle of long-period comets into the inner system, punctuated by occasional bursts after stellar encounters. When we see a bright, long-period comet, we are watching the end of a story that was mostly written in darkness. Even the planets play a role after the long-period comet arrives, because the first pass is not the end of the story. Jupiter and Saturn can capture a fraction of these visitors into shorter period orbits, or they can eject them entirely. A long-period comet that survives the inner system may return as a different object, with a different period and a different fate. In that sense, the two families are connected because the inner giants can convert one kind of visitor into another. Now we shift from the comets we see to the objects that rarely come close. Distant trans-Neptunian objects keep their perihelia far beyond Neptune's strongest reach, as if they were lifted away from the usual scattering zone. Their orbits look detached, and that detachment is a dynamical statement rather than a mere distance measurement. On a plot of perihelion distance versus semi-major axis, they sit in a region that looks like it should be empty, yet it is not. Detached does not mean untouched, and that is where the puzzle deepens. If Neptune cannot easily scatter them today, then something either acted in the past or is acting gently in the present. Their orbital elements become a kind of fossil record, preserving the imprint of whatever sculpted them. The question is, what kind of sculptor leaves a signature without obvious close encounters? This is where the detective story begins, because patterns appear in the data and invite interpretation. A subset of extreme trans-Neptunian objects, or ETNOs, show unusual clustering in their orbital orientations. Their long axes and perihelion directions seem to align more than chance would suggest, and that alignment is difficult to ignore once you plot it. The moment you draw the arrows on a heliocentric map, the pattern feels less like noise and more like intent. Perihelion alignment means their closest approach points point roughly the same way in space, like arrows that refuse to spread evenly around the Sun. It also means their orbital orientations are not uniformly distributed, which is what simple random scattering would tend to produce. If real, that is a dynamical fingerprint left by a persistent perturber, because persistence is what maintains coherence against chaos. Without a shepherd, differential precession should smear the pattern out over time. The Planet 9 hypothesis is one proposed perturber, and it is framed as a conservative idea in a dramatic costume. It suggests a massive planet, perhaps several Earth masses, on a distant, elongated orbit that is tilted relative to the planetary plane. Over long times, it could shepherd ETNOs into aligned configurations, maintaining patterns that would otherwise disperse. The hypothesis is bold in implication, yet it uses familiar gravity rather than exotic forces. The mechanism is not magic, it is secular sculpting, which is a technical phrase for slow, averaged gravitational influence. A distant planet can impose coherent torques that accumulate over many orbits, even if close encounters are rare. Those average torques can maintain clustering even when individual objects move unpredictably from year to year. In plain terms, the perturber does not need to hit the objects, because it can steer them by consistently leaning on their orbital orientation. In this view, Planet 9 also helps explain why some objects are both distant and detached, because it offers a way to raise perihelia. It can push bodies away from Neptune's scattering zone, making them harder for Neptune to reach and harder for us to detect. It can also create stable islands where aligned orbits persist for long spans, like eddies in a slow gravitational current. The outer solar system becomes less like a simple disk, and more like a multi-layered dynamical ecosystem. The idea carries a deeper implication about what counts as the solar system's architecture. We often imagine the planets as the only organisers, with small bodies as debris that merely responds. Planet 9 would blur that line, because a new planet would be both debris' sculptor and a product of the same early history. If it exists, it would force a rethink of how efficiently the young solar system built, scattered, and retained mass. But the narration must keep the uncertainty honest, because the evidence is contested and the debate is methodological. Observational bias can manufacture apparent clustering when surveys look preferentially in certain sky regions, and the outer solar system is notoriously hard to survey uniformly. The faintest objects are found where we search, and we search unevenly, constrained by telescope time, weather, and the glare of the Milky Way. Even the seasons matter because some sky regions are simply more accessible at night during certain months. Bias is not a dismissal. It is a competing explanation that must be tested with careful modelling. The sky coverage of surveys is patchy, and detection efficiency depends on brightness, motion rate, and background star density. If we only detect objects near perihelion, we sample orientations unevenly, because perihelion is where they are brightest and fastest. In other words, the pipeline of discovery has its own selection effects, and those effects can masquerade as celestial design. So the question becomes methodological as well as astronomical, and it is a question about inference under imperfect data. Do the alignments survive when we model the selection effects carefully, using simulated survey footprints and realistic detection thresholds? Do they persist as new objects are found in new survey regions, or do they dissolve as the sample grows? The outer solar system is a place where small number statistics can mislead, and where patience is required to separate pattern from coincidence. Even with that caution, the hypothesis matters because it reframes the solar system's outer boundary as an active, structured region. A ninth planet would not be a footnote beyond Neptune, tucked away like a forgotten label. It would be a new organising mass in the outer system, and mass is what writes the long-term rules. The most important consequence would not be a new dot on a poster, but a new set of stable and unstable pathways. Planet 9 would reshape the boundary story in 3 ways, and each one changes how we picture the map. It would extend the region where planets matter dynamically, because its secular reach would operate far beyond Neptune. It would alter the pathways that feed the scattered disk and perhaps the inner Oort Cloud, changing the supply chain that delivers comets. It would also change how we interpret detached, because detachment might become a sign of shepherding rather than isolation. It would also break the neat 8-planet diagram that still anchors public intuition and even scientific shorthand. The solar system would look less like a tidy set of rings and more like a hierarchy of fading control, where influence declines gradually rather than ending abruptly. The outer system would become a zone of competing sculptors, each dominant in a different regime. In that hierarchy, Neptune is not the final word, it is simply the last clearly visible editor. Those sculptors already include Neptune, passing stars, and the galactic tide, and they operate on different timescales. Neptune acts through repeated encounters and resonances, shaping orbits in a disk-like context. Passing stars act episodically, and the galactic tide acts continuously, both becoming more important as distance increases. The farther you go, the more the solar system begins to feel like a participant in the galaxy rather than a self-contained machine. Planet 9 would add a local, persistent hand in the same distance regime where the other influences begin to matter. The combined picture would be a layered gravitational landscape, not a single edge and not a single story. The question becomes less about where the solar system ends and more about which influence dominates at a given distance. That is a subtle shift, yet it changes the emotional tone of the map, from boundary to gradient. Now we introduce a new anomaly that forces a rethink, because anomalies are where models are tested rather than admired. In the documentary's timeline, a 2026 report claims an atmosphere around a tiny distant world, far beyond the familiar planets. The object is small enough that an atmosphere should be difficult to keep, which makes the claim a direct challenge to expectations. If true, it is not just a curiosity, because it suggests that the outer inventory can still behave like an active system. On screen, we imagine a faint point of light against a dense star field, and then a subtle halo revealed through careful processing. The atmosphere is not a blue sky or a thick blanket, but a whisper in a spectrum, an absorption feature, a slight broadening, a hint of gas. The drama is not in how it looks, but in what it implies. A few pixels of excess light can become a question about physics at the edge of sunlight. Atmospheres are hard to retain for three simple reasons, and each one is grounded in basic physics. Low gravity makes escape easier, especially for lighter molecules whose thermal speeds are higher. Cold temperatures reduce vapor pressure, yet they also encourage volatile freezing and atmospheric collapse, turning gas into surface frost. In that cold regime, an atmosphere can behave like a seasonal deposit, migrating from one hemisphere to another as illumination changes. Solar wind and ultraviolet radiation can strip and dissociate gases, especially when a body lacks a strong magnetic field. UV photons can break molecules apart, and the resulting atoms can be swept away by charged particles. Even a thin atmosphere can be eroded when it is exposed and unprotected, and time is relentless on billion-year scales. The outer solar system is quieter than Earth's neighbourhood, yet it is not gentle, because erosion is slow and cumulative. So an atmosphere report becomes a stress test for our thermal models and for our assumptions about distant small bodies. If the detection is real, something is replenishing gas faster than it is lost, at least intermittently. That implies active volatile behaviour where we expected deep dormancy, and it forces us to ask what heat sources and transport mechanisms we overlooked. It also invites a sharper question. How many inactive bodies are merely waiting for the right geometry to reveal themselves? One mechanism is volatile outgassing from subsurface pockets, where trapped ices can remain insulated beneath a porous crust. A small heat source can be enough if the volatile is extremely sensitive to temperature, because sublimation rates can rise sharply with modest warming. Even a tiny seasonal shift can move nitrogen, methane, or carbon monoxide from solid to gas, and the gas can find fractures to the surface. The process can be episodic, because a sealed pocket may vent, reseal, and vent again as the surface evolves. Another mechanism is seasonal sublimation driven by orbital eccentricity, which changes the object's distance from the Sun and therefore its received sunlight. If the object's orbit is elongated, peak heating near perihelion can release gas and loft dust. The atmosphere could then collapse again as the object recedes, freezing out onto the surface in a cycle that is slow but repeatable. In deep time, those freeze-thaw cycles can sort surfaces, redistribute volatiles, and build layered deposits that preserve a climate record. A third mechanism is transient coma-like behaviour that mimics an atmosphere, and the distinction can be observationally subtle. A weak, persistent leak of gas and dust can create a bound-looking envelope, especially if the outflow speed is low. In that case, the boundary between atmosphere and comet activity becomes ambiguous, and classification becomes a question of degree. The object may not be a classic comet with a long tail, yet it could still be shedding material into space in a controlled, low-energy way. The anomaly also forces us to revisit volatile retention assumptions, which are often summarized too casually as small equals inert. We often treat small, distant bodies as inert because they are cold and small, but cold does not always mean inactive. Pluto already challenged that with its nitrogen cycle and hazes, and this 2026 report extends the challenge to even smaller scales. If a tiny body can hold gas even briefly, then it can also exchange material with space, and that exchange changes how its surface ages. If tiny bodies can briefly hold gas, then the comet pipeline gains a new stage that sits far from the Sun. Objects can switch between storage and activity without entering the inner solar system, which means chemistry can proceed in places we once treated as static. The outer region becomes chemically dynamic even in deep cold, and that dynamism may affect how surfaces evolve over time. It also suggests that some comets may begin their activation long before they ever become visible to us. At this point, we address the word dark, because it invites confusion and can derail the story. Dark matter is not expected to shape Kuiper Belt dynamics at these scales, because its density in the solar neighbourhood is far too low. The gravitational field here is dominated by the Sun, planets, and known baryonic mass, and the equations do not need exotic ingredients. If we see unexplained structure, the first suspects are ordinary masses on hard-to-detect orbits. The darkness we mean is literal and observational, and it is the kind that telescopes struggle against. Most of the region is unlit, and most objects are unseen. Because they are small, distant, and reflect very little sunlight, the mass we do not catalogue is still ordinary matter, hidden by distance and faintness, and revealed only through statistical inference. In practical terms, an object can be there in abundance and still be invisible, simply because it is too far, too dark, and too slow to stand out. That distinction matters because it separates astrophysics from speculation, and it keeps the mystery grounded. Planet 9, if it exists, is ordinary matter on a difficult orbit, not an exotic particle cloud. The mystery is not new physics, it is incomplete census and subtle dynamics, plus the sobering limits of observation. The outer solar system remains one of the few places where a planet-sized body could plausibly hide in plain sight. Now we tie the threads together into a single pipeline narrative, and we keep the chain of custody clear. The Kuiper Belt and scattered disk provide the raw inventory of icy bodies, assembled from the leftovers of planet formation. Neptune and resonances sort that inventory into stable niches and unstable pathways, quietly deciding which objects remain stored and which become travellers. In this sorting, stability is not a moral category, it is a timescale, and the timescale decides whether an object becomes a comet. Jupiter and Saturn then act as the inner filter, capturing some bodies into short-period orbits and ejecting others into interstellar space. The Oort Cloud, if it exists as inferred, supplies long-period comets through external triggers like passing stars and the galactic tide. Planet 9, if real, would add a new sorting layer between disk and shell, reshaping the supply chain that feeds both comet families. The pipeline becomes a connected system of reservoirs, gates, and slow talks, rather than a set of isolated regions. The 2026 atmosphere anomaly becomes a warning sign in the middle of that chain, because it suggests our thermal and volatile models may be missing key processes. It also suggests that distant objects can still surprise us with active behaviour, even when sunlight is weak. If activity can occur out there, then the pipeline is not only dynamical, but also chemical, and the two stories may be linked. A body's orbit decides where it goes, but its volatiles decide how it responds when it gets there. This is where we return to the central question about scale and boundaries, because the pipeline keeps pointing outward. We keep calling the Kuiper Belt an edge because it is the farthest region we have visited closely, and because it is where the familiar planetary map fades. Yet the comet pipeline keeps pointing outward, toward reservoirs we infer rather than see, and toward forces that operate on timescales longer than civilizations. The edge turns out to be a threshold of knowledge, not a physical wall. Comets are evidence that the solar system's frontier is not a line, and not even a single region. It is a set of pathways that connect disk to shell and shell to inner space, with planets acting as gates and the galaxy acting as a slow hand. The architecture is defined by weak forces acting for long times, and by rare encounters that leave permanent marks. When a comet appears, it is a message from that architecture, written in motion and illuminated by the sun. Transition. If comets and anomalies hint at something farther, the ultimate source region is not a belt. It is a shell, and it may dwarf everything we have discussed, both in size and in the sheer number of bodies it could contain. We end with the scale threat hanging in the air, because scale changes the meaning of every boundary. The Kuiper Belt is a doorway that feels like a wall, a region where our probes have flown and our telescopes have begun to count. The Oort Cloud is the footprint that makes the doorway look small, a vast implied structure whose existence is written in the trajectories of rare visitors. The more we follow the pipeline outward, the more the solar system resembles a fading sphere of influence rather than a neat set of rings. In the next chapter, we leave the disk geometry behind and we let the solar system become three-dimensional in the most literal way. We follow the evidence into a spherical darkness where the galaxy's pull becomes part of the solar system's story. The question stops being where the planets end and becomes where the sun's influence dissolves. The Kuiper Belt still feels like the edge because we can plot it, label it, and argue about its subgroups. The Oort Cloud is where plotting becomes inference, and inference becomes unsettling scale, because the map turns into a probability field. We leave the last measured worlds behind and keep the unit the same. The astronomical unit stays familiar while the distances stop behaving like geography, and the mind loses the comfort of landmarks. Even the language shifts because out there stops meaning a direction and starts meaning a regime. At 50 AU, the sun is weak but present, and spacecraft still navigate by it with stable radio links and predictable ephemerids. The sunlight is thin, yet it still casts shadows across a probe's antenna and keeps solar panels honest. In wide shots, the sun is still a bright coin, and the sky still feels like a place you could point to. At a few hundred AU, the sun is no longer a dominant lamp in the sky, but it still defines direction. The geometry remains readable, because the sun's position still anchors a spacecraft's attitude and the timing of its signals. At thousands of AU, the sun becomes a bright star behind you, not a lamp ahead, more like a memory than a source. Visually, the outer solar system stops looking like a place and starts looking like a diagram. The planets vanish into a tight cluster near the center, and the empty black between tick marks becomes the main character. The camera lingers on that emptiness, because emptiness is what the Oort Cloud is made of, space first, objects second. The Oort Cloud is a hypothesis built to explain a pattern, not an image. It is a distant population of icy bodies bound to the sun, distributed roughly as a sphere or thick shell, where roughly carries most of the honesty. If it exists, it is less like a ring and more like a halo, with density that fades rather than ends. The typical framing begins at a few thousand AU and extends to tens of thousands, although the inner boundary is debated. Some models push the outer reach toward 100,000 AU, where the sun's gravity competes with the galaxy and loses clean authority. In that territory, even defining outer edge becomes a question about time, not distance. That number is not just large, it is a change in category. 100,000 AU is a meaningful fraction of a light year, and it approaches interstellar space in practice, even if the object remains technically bound. A bound orbit can still be fragile, and fragility is the theme at this scale. Put another way, the Oort Cloud would occupy a region where the sun is no longer the only architect. The Milky Way's tidal field, nearby stars, and the sun's own motion through the galaxy begin to matter as much as planets. The solar system becomes a participant in a larger gravitational ecology. This is the documentary's scale apex because the ratio is brutal. The Kuiper Belt's main band spans tens of AU, while the Oort Cloud may span tens of thousands, turning a belt into a halo that dwarfs everything we have seen. The familiar architecture of orbits becomes a faint inner ornament inside a vast sphere. If you shrink the solar system to a handheld map, the Kuiper Belt looks like the border. The Oort Cloud turns that border into a doorway, and the doorway opens into a volume, an enormous, dim, three-dimensional territory. The mind expects an edge, but gravity prefers gradients. In visuals, the camera pulls back until Neptune's orbit becomes a hairline ring, and the Kuiper Belt becomes a faint smudge. Then the frame keeps widening, and the smudge is swallowed by a translucent sphere that barely fits on screen. The sphere is not bright. It is suggested, like breath on glass. The evidence begins with long-period comets, which arrive with near-parabolic energies. Their semi-major axes imply they spent almost all their time extremely far away, moving so slowly that a single orbit can outlast civilizations. When we notice them, we are catching the last moments of a journey that was mostly darkness. A near-parabolic orbit is a clue about binding energy, because parabolas sit at the edge between bound and unbound trajectories. In orbital mechanics terms, the specific orbital energy hovers near zero, so a small perturbation can decide the outcome. When a comet arrives with that kind of energy, it suggests it was nudged inward from a reservoir where the sun's grip is barely sufficient. More important than energy is direction, because direction is harder to fake. Long-period comets arrive from all over the sky, with inclinations that do not cluster near the ecliptic, and that isotropy is the fingerprint. The sky itself becomes the dataset, with every arrival acting like a compass needle. If the source were a flat disk like the Kuiper Belt, arrivals would be biased toward the disk plane. A disk can scatter and thicken, and resonances can stir it, but it struggles to feed the inner system isotropically without leaving a directional preference. The ecliptic would show itself as a favoured corridor, and it does not. An isotropic arrival distribution points to a roughly spherical reservoir. A sphere has no preferred plane, so it can deliver comets from any direction with equal likelihood, above, below, or sideways, relative to the planetary disk. The implication is subtle but powerful, because geometry is a form of evidence. This is the core logic Jan Oort formalised in 1950, using comet orbit statistics and the tools available at the time. The cloud was not proposed as decoration, but as the simplest reservoir consistent with the data, and simplicity matters when the sky is your laboratory. Oort's paper turned scattered sightings into a coherent dynamical argument. Oort's work came after centuries of comet watching, when comets were finally treated as orbiting bodies rather than omens. By the mid-20th century, improved astrometry and better orbit determination made it possible to compare many comets as a population, not as isolated curiosities. The change was cultural as well as technical, because it replaced fear with measurement. The argument is not perfect because the data are sparse and biased. We discover comets when they brighten, and brightness depends on perihelion distance, volatile content, dust production, and how a comet's surface evolves after repeated heating. A catalogue is never just a list. It is a list filtered by physics. A comet that passes close to the Sun can flare dramatically, while another of similar size might stay dim if its volatiles are buried. Jets can turn on and off as sunlight reaches new terrain, and dust can either cloak the nucleus or expose fresh ice. That selection effect means our sample is not a clean census, and the sky we observe is filtered by physics. Even so, the sky distribution remains difficult to explain without a three-dimensional source. The Oort Cloud is the best-fitting shape for the long-period comet pipeline because it naturally produces arrivals that do not respect the planetary plane. The simplest geometry keeps winning, even when the statistics are imperfect. In animation, the difference is stark. Short-period comets trace a band near the ecliptic, like sparks skimming a record groove, while long-period comets streak in from every angle, like needles thrown at a sphere. The contrast is immediate, and it makes the inference feel almost visual. The next step is structure inside the structure, because a single cloud may be two regimes. Many researchers distinguish an inner reservoir and an outer reservoir, separated by binding strength and by how easily external forces can reshape their orbits. The division is not a wall, but a change in how the same forces behave. The inner Oort cloud is often called the Hills cloud, after Jack Hills, who argued for a deeper storage region. It is more tightly bound to the Sun, with semi-major axes perhaps in the thousands to tens of thousands of AU, and it may hold the most resilient inventory. In this inner zone, the Sun still feels like the main owner, not a distant landlord. The outer Oort cloud is more weakly bound, with semi-major axes commonly framed as tens of thousands. In that regime, tiny perturbations can change perihelion dramatically over long times, because the orbit is so large that small torques accumulate. The object's speed of aphelion is so low that a gentle nudge can rewrite its future. Binding strength matters because it sets the rules of survival. A comet in the inner cloud is harder to steal, harder to unbind, and harder to disturb, while a comet in the outer cloud lives on the edge of the Sun's ownership. The difference is not just distance, but how quickly order turns into drift. The inner reservoir matters because it can be a long-term bank. It can resupply the outer cloud after stripping events, and it can preserve memory of early scattering, like a vault that keeps the oldest signatures intact. If the outer cloud is weathered by the galaxy, the inner cloud may still remember the early solar system. The outer reservoir matters because it is easy to trigger. It can feed comets inward when the galaxy and passing stars talk orbits, even if the planets are far away, because the outer cloud is already close to instability. It is the part of the kingdom most likely to send messengers and most likely to lose citizens. Both components remain uncertain because we have never directly detected a single Oort cloud object. Distance makes them faint, and their motion is so slow that surveys struggle to separate them from stars, especially when the background is crowded. The irony is sharp. A structure that may contain trillions remains observationally anonymous. At tens of thousands of AU, reflected sunlight is vanishingly small. The inverse square law is merciless, and by the time you reach those distances, the sun's light is diluted into something closer to a weak studio lamp across a continent. Even a large icy body would look like a speck of charcoal against a crowded sky. Thermal emission is also weak because these bodies are cold, small, and far. Their surfaces would sit only a few degrees above the temperature of interstellar space, radiating mostly in the far infrared where detection demands exquisite sensitivity. In plain terms, they are not only dim, they glow in a colour our eyes cannot see. Direct detection is not only a telescope problem, it is a time problem. An object that far moves so slowly that confirming an orbit can take years of careful astrometry, and the parallax you rely on becomes tiny. The sky's background is a fixed tapestry, and the Oort Cloud would move like dust on glass. Even if you see a faint dot, you must prove it is not a distant star or a galaxy. That proof requires repeated measurements, precise calibration, and patience, because the sky does not hurry for human schedules. The cloud hides in the same way deep time hides, by being too slow to notice. So the Oort Cloud remains a kingdom inferred from visitors, like a coastline inferred from driftwood. The comets are the only routine messengers that cross the gap, and they arrive already altered by the journey. We study the messenger's scars, and from those scars we imagine the homeland. When a long-period comet enters the inner solar system, it is not just moving through space. It is crossing environments, warming rapidly, shedding gas and dust, and turning invisible ice into a visible atmosphere that we can finally notice. The coma is a temporary sky, built from material that was locked away for eons. But comets do not fall inward by themselves, because most Oort orbits are stable in the sense of not intersecting the planets. Something must change their angular momentum so perihelion drops into the inner system, and that something is usually gentle, not violent. The trigger is often a slow rearrangement, not a dramatic collision. Two external sculptors dominate the trigger story. One is the galactic tide, and the other is passing stars, with molecular clouds as rare but powerful variants, and each operates on a different rhythm. One is continuous, the other episodic, and both are indifferent to our calendar. The galactic tide is the Milky Way's gravity acting differentially across the solar system. The near side and far side feel slightly different pulls, and that difference slowly torques distant orbits, like a long lever being nudged at its end. The effect is tiny at any moment, yet persistent in a way the planets cannot ignore. It is not a sudden shove, it is a persistent bias that never turns off. Over millions of years it can raise or lower perihelia, turning safe distant loops into sun-crossing trajectories, even while the semi-major axis remains enormous. The orbit's size stays the same, while its closest approach quietly changes. A useful metaphor is a gentle but relentless hand, because the force is weak and the timescale is enormous. In the Oort regime, weak forces win because the binding is weak, and because time gives them endless opportunities. The galaxy does not need strength when it has patience. The tide also has geometry, because the galaxy has a disk and the sun oscillates through it. The direction of the tidal torque depends on the sun's position relative to the galactic plane, and on the local distribution of mass, stars, gas, and dark matter. The Oort Cloud is therefore sensitive to where the sun is in its long galactic journey. That means comet injection is not perfectly steady. It can vary as the sun moves through denser regions, and as the tidal field changes with galactic radius and local mass distribution, producing subtle long-term modulation. The result is not a metronome, but a background rhythm with slow swells. In a visual sequence, the solar system rides a slow wave through the Milky Way's disk. The Oort Cloud, drawn as a faint shell, flexes slightly as the background gravitational field changes and a few trajectories bend inward like threads pulled by an unseen current. The motion is almost imperceptible, until you compress millions of years into seconds. Passing stars add punctuated events to the slow tide. A star does not need to come near Neptune to matter, because an Oort orbit is so large and fragile, and the encounter acts on the farthest, loosest members first. In this realm, near means thousands of AU, and that is enough. A flyby at thousands of AU can still reorient a comet's orbit. It can change perihelion distance, change inclination, and sometimes unbind the object entirely, turning a bound member into an interstellar drifter. The encounter is a brief conversation between two gravitational fields, and the comet pays the price. The effect depends on the star's mass, speed, and closest approach, but also on timing. A comet near aphelion moves slowly, and that slowness makes it vulnerable, because a small velocity change there can translate into a large change in where it later crosses the inner system. The lever arm is enormous, so the smallest push can matter. These encounters also explain how the cloud could have been populated. Early in solar system history, the giant planets scattered icy bodies outward, and stellar encounters helped lift and randomize their orbits, preventing many from simply returning to the planetary region. Without that lifting, the scattering would have been less like storage and more like a temporary fling. The scattering begins with close gravitational encounters, where a small body trades energy with a planet. Jupiter and Saturn can eject objects outright, while Uranus and Neptune can push them outward into long, elongated orbits that become the raw material for the cloud. Each encounter is a gravitational slingshot, and the direction of the slingshot decides the object's fate. The Sun likely formed in a birth cluster where close stellar passages were more common. In that environment, the cloud could be built efficiently, but it could also be trimmed or distorted, because the same encounters that lift orbits can also strip them away. The early solar system may have been both a factory and a battlefield. This cluster context adds a historical layer to the cloud's mystery. The Oort Cloud, if it exists, is not only a product of the Sun, but also a relic of the Sun's earliest neighbourhood, when the night sky was crowded with sibling stars. The cloud becomes a surviving trace of a place we can no longer visit. Molecular clouds are less frequent but can be significant because of their mass. A passage through a dense region can increase perturbations, potentially producing comet showers or stripping the outer cloud, and the timescale can be brief compared with galactic cycles. Even diffuse gas has gravity, and in bulk it can behave like an invisible mountain. Here the visuals can shift from stars to mist. The solar system drifts through a dark, textured nebula, and the outermost orbits ripple as if a pressure wave passed through, even though the force is gravity alone. The scene feels like weather, yet it is celestial mechanics. This is where the Oort Cloud becomes a record of environment, not just of formation. Its present shape would reflect both the early scattering by planets and the long-term galactic neighbourhood, with every encounter leaving a statistical scar. The scars are not carved into rock, they are carved into probability. The terrifying implication is that the solar system's outskirts are not controlled only by the Sun. At tens of thousands of AU, the galaxy becomes a co-author of our boundary, and the Sun's authority becomes conditional. The kingdom exists, but it exists under a larger empire. The Kuiper Belt is shaped mostly by Neptune and resonances. The Oort Cloud is shaped by Neptune's ancient scattering, plus the galaxy's slow torque and random stellar flybys, which continue to edit the population long after formation. The editing never ends, it only changes pace. That difference is structural as well as spatial. The Kuiper Belt is a thick disk with a preferred plane, while the Oort Cloud is a volume with no preferred direction, and that volume is where up and down lose meaning. In a sphere, orientation is local, not universal. The disk-to-sphere transformation is the key conceptual leap. It tells us that the solar system's architecture is not a set of rings, but a transition from planar formation to three-dimensional storage, driven by gravitational chaos and external tides. The system begins as a disk of gas and ends perhaps as a halo of ice. We now address the hardest part of the story, which is that the cloud might not be random. For decades it was described as a spherical swarm, dynamically heated and largely featureless, because that was the simplest end state. Simplicity was practical, because the cloud itself refused to be seen. Recent modelling and survey-driven inference suggest a more organised inner region. The claim is not that we have imaged a spiral, but that simulations and orbital statistics allow it, and that the math can produce persistent patterns. The language stays careful, because the evidence is indirect and the uncertainties are real. In these models, the inner Oort cloud can develop a spiral-like density pattern. The structure is subtle, long-lived, and tied to how objects were emplaced and later torqued, especially if the early population shared correlated orbital elements. The pattern would be faint, like a watermark that only appears under certain lighting, A spiral can emerge when a population shares correlated orbital phases and precession rates. Over time, differential precession wins that correlation into a pattern that looks like architecture, even though each object still follows its own Keplerian path. The spiral is not a solid arm but an overdensity, more likely here than there. To make that plain, imagine many elongated orbits whose long axes slowly rotate. If they rotate at slightly different rates, the ensemble can form a wrapped, spiral-like overdensity, an emergent pattern drawn by time rather than by a sculptor's hand. What looks like design is really the accumulation of tiny differences. The idea matters because it suggests memory. A purely randomized cloud would erase early conditions, while a structured inner cloud could preserve an imprint of formation and early stellar environment, like a fossil that still carries the grain of ancient wood. If the imprint is real, it is a message from the sun's first million years. This is still emerging evidence, and it is framed with caution. The statistics are difficult, the selection biases are severe, and the models depend on assumptions about early scattering and cluster history, which are themselves uncertain. The honest posture is provisional because the cloud does not yet offer direct confirmation. But even the possibility changes the tone of the cloud. The Oort cloud stops being only a fog of leftovers and becomes a potential dynamical fossil with internal design. Faint, indirect, but conceptually profound. It invites a question that feels almost philosophical. How much structure can survive in the dark? If the inner cloud has structure, it could also affect comet delivery. Certain regions of phase space could be more efficient at feeding perihelia inward under tides and stellar nudges, creating preferred pathways through an otherwise vast reservoir. The pathway would not be a road, but a statistical current. That would mean the long-period comet flux is not just a random drizzle. It could carry weak anisotropies or time variability linked to the cloud's internal organization, and those subtleties would be easy to miss without long observational baselines. The sky might be whispering patterns that we have not listened to long enough. Here, we reconnect to the documentary's central question about comparing belt and cloud. The Kuiper Belt is an observed population with mapped subgroups, while the Oort Cloud is an inferred population with debated substructure, and that contrast defines the mood. One region is cartography, the other is forensic reconstruction. The Kuiper Belt scale is intimidating when you first learn it, because it pushes beyond planets. The Oort Cloud scale is unsettling because it makes the Kuiper Belt feel close, like the shoreline of a much larger ocean. The shoreline is real, but it is not the end of the water. The Kuiper Belt is where sunlight is faint and travel times are long. The Oort Cloud is where sunlight is almost irrelevant, and orbital periods can exceed human history by orders of magnitude, turning motion into something nearly static. In that stillness, the solar system feels less like a machine and more like a slow field. The Kuiper Belt is where a spacecraft can still send back images within a day's light time. The Oort Cloud is where even light time becomes a narrative tool, because the distances approach a year, and now becomes a stretched concept. A command sent today could arrive in a different chapter of a human life. We also return to the earlier boundary argument, because the Heliopause is not the ending. Voyager crossed the Heliopause and entered interstellar plasma, yet it remained deep inside the Sun's gravitational domain, still falling around the Sun in a vast orbit. The craft changed environments, but it did not change owners. If the Oort Cloud exists, then the Heliopause is a weather line, not a border. It is the edge of the solar wind's bubble, not the edge of the solar system's material reach, and that distinction changes the story's ending. The wind stops, but gravity continues. That forces a definition question that cannot be avoided. Is the solar system defined by plasma, by planets, by gravity, or by the farthest bound debris? And which definition matches what we intuitively mean by ours? The discomfort comes from realizing that each definition draws a different map. Gravity gives the most expansive answer, and it is also the most haunting. Under that definition, the solar system is not a neat map of orbits, but a fading sphere of influence, thinning until it becomes indistinguishable from the galaxy. The edge is not a line, it is a loss of certainty. At the outer cloud, the Sun's grip is so weak that the galaxy can steal objects away. The boundary becomes probabilistic, defined by stability timescales rather than a line, and by whether an orbit survives the next few billion years. Ownership becomes a question of how long a bond can resist disturbance. This is where the phrase approaching interstellar space becomes literal. An object at 100,000 AU is still bound. Yet it lives in a regime where a small nudge can end that bond, and belonging becomes temporary. The object is a citizen on the frontier, always at risk of exile. The Oort Cloud therefore blurs the difference between belonging and escaping. It is a reservoir of potential departures as much as a reservoir of potential arrivals, and that dual role is part of its eerie elegance. A cloud that feeds comets inward can also bleed material outward. We can also connect this to ejection, because the same scattering that built the cloud also threw many bodies out entirely. The solar system likely lost far more icy bodies than it kept, and those lost bodies now drift between stars as unclaimed debris. In that sense, the Sun has already exported part of itself into the galaxy, so the Oort Cloud is not only a storage shell, it is a remnant of a violent filtering process. It is what stayed bound after the early giant planets flung material outward, and after the galaxy tested that material with tides and encounters. The cloud is what survived repeated attempts at erasure. That remnant may contain enormous numbers of objects, perhaps trillions, depending on size distribution assumptions. The mass is uncertain, but the count could dwarf the Kuiper Belt's known inventory, because small bodies are expected to be far more numerous than large ones. The kingdom may be populous, even if its citizens are individually insignificant. Uncertainty is part of the story, not a weakness to hide. The Oort Cloud is a model constrained by comet statistics, by dynamical simulations, and by the physics of perturbations, and each constraint is informative even when it is incomplete. In science, an unseen structure can still be real if it explains what we do see. Its inner edge is uncertain because we do not know where the scattered disk ends and the cloud begins. Its outer edge is uncertain because we do not know where the galaxy's tide strips more than it stores, and because the Sun's environment changes over time. Even the transition zones may overlap, blurring categories we would prefer to keep separate. Even its shape is uncertain because a perfect sphere is an idealization. The galactic tide and stellar encounters can flatten, stretch, or warp the distribution over time, and the result may be a thick, slightly distorted shell rather than a clean globe. The cloud could be subtly squashed toward the galactic plane, an imprint of the larger field. A thick shell is therefore a safer mental model than a crisp sphere. The cloud is likely lumpy, structured by history, and constantly being reworked by external gravity, slowly, quietly, and without any visible boundary marker. The kingdom has no walls, only gradients. The key point is that the Oort Cloud makes the solar system three-dimensional in the most extreme way. It turns the outer system from a disk story into a halo story, and it makes the Sun's domain feel less like a system, and more like a fading influence. The farther you go, the less the word system seems to fit. It also reframes the Kuiper Belt as the inner rim of a much larger domain. The belt is the farthest region we have seen, but it is not the farthest region the Sun may own, and that gap between seen and owned is the chapter's tension. We can map the shoreline, but the ocean remains inferred. This is the climax beat where numbers become emotional. Thousands of AU feel like distance, tens of thousands feel like isolation, and 100,000 feels like the Sun dissolving into the galaxy, becoming just another star among many. At that point, scale becomes mood, and mood becomes meaning. We now tighten the causal chain so the audience can hold it. Planets scatter icy bodies outward, trading energy in close encounters that stretch orbits into long ellipses. The birth cluster and early stellar encounters lift and randomize orbits, turning a disk-borne population into a halo. The same physics that builds the cloud also ensures it will never be perfectly still. Then the galactic tide and later flybys keep stirring. Over deep time, that stirring both injects comets inward and strips others away, and the cloud becomes a dynamic boundary rather than a static shell. A boundary that moves is harder to picture, but it may be closer to the truth. Out of that chain comes a shell that can feed comets inward. Those comets arrive isotropically, and their directions are the signature that the shell exists, even when the shell itself remains unseen. The evidence is written in trajectories, and trajectories are the language of gravity. Out of that same chain may come structure in the inner cloud. A spiral-like pattern would be a surviving imprint, suggesting the cloud is not only stirred, but also organized, and that organization could be a clue to the Sun's earliest environment. If we could read that imprint, we might read the Sun's childhood. The Oort Cloud becomes the Sun's invisible kingdom because it is vast, bound, and mostly unreachable. It is also invisible because our best instruments still struggle to see a single resident, and because the residents move like distant clock hands. The kingdom's existence is felt, not observed, and that is what makes it haunting. Yet the kingdom announces itself when a long-period comet appears. A bright visitor in the inner sky is the end of a million-year orbit, triggered by a tide or a passing star, and the visitor's sudden brilliance hides its long, cold exile. The spectacle is brief, but the backstory is almost incomprehensibly long. In a visual beat, the comet's nucleus is a dark pebble wrapped in a glowing coma. The tail streams away from the sun, and the narration reminds us that this spectacle began in darkness so deep that even the sun was only a star. The camera can pull back from the bright tail to the empty sky it came from, an emptiness that is not empty. That visitor is also a reminder that the solar system is not sealed. The same processes that send comets inward also send bodies outward, and some of those bodies never come back, becoming part of the galaxy's own debris field. The boundary is porous, and porosity is a kind of vulnerability. So the Oort Cloud is both a boundary and a leak. It is the farthest storage of solar system debris, and it is the region most exposed to being stripped into interstellar space, where home is no longer a meaningful label. In the outer cloud, the difference between resident and refugee can be one encounter. This is the chapter's final boundary transition. If the Oort Cloud is real, then the Heliopause is only a change in wind, and the planets are only the inner landmarks, and the true edge is a gradient written in gravity. The ending is not a stop, it is a fade. What we call the solar system becomes a gradient of control, fading from planets to disk to shell to galactic field. The ending is not a wall, it is a slow surrender of dominance, measured not in miles but in how easily the galaxy can interfere. The question becomes uncomfortable. Where does ours end if influence is always negotiable? Transition. We have followed the evidence to the largest implied structure the Sun can hold. Now we ask what it means to end a system that dissolves rather than stops, and whether our definitions are about physics or about comfort. In the final chapter, we will confront definitions and consequences. We will compare the Kuiper Belt's mapped edge to the Oort Cloud's inferred reach, and decide what border is honest, when the universe refuses to draw clean lines. Voyager 1 is still moving outward, still transmitting, still rewriting what we mean by far, even as its signal thins into a whisper. Its journey is not toward a planet, but toward a boundary made of plasma, an edge defined by fields, particles, and pressure. In wide shots, the probe is almost nothing against the black, a slow-moving speck with a dish turned homeward, yet the emptiness is not empty, and the darkness is not still. Space is threaded with magnetic lines, sparse atoms, and the residue of ancient explosions. The Heliosphere is the sun's bubble of charged particles and magnetic field, inflated by the solar wind. It is an atmosphere of space weather, not a container for the solar system, and it responds to the sun's cycles like a lung. The solar wind itself is a plasma, mostly protons and electrons, streaming outward from the corona at hundreds of kilometers per second. It carries the sun's magnetic field with it, stretched into the Parker spiral by rotation, an invisible pinwheel that fills the planet's orbits. As the solar wind streams outward, it eventually slows from supersonic to subsonic flow. That slowdown is the termination shock, where the wind first collides with the pressure of the surrounding medium, and where kinetic energy becomes heat and turbulence. A shock like this is not a cliff you could see, but it is a real physical transition. In the data, it appears as abrupt changes in particle speeds, densities, and temperatures, signatures of a flow forced to break in deep space. Beyond that shock lies the heliosheath, a turbulent region of slowed solar wind and tangled fields. It is a mixing layer where the sun's outflow is compressed, heated, and redirected, and where eddies of plasma can persist for years. If we could visualize it, the heliosheath would look like a stormy sea rendered in magnetism. Filaments would fold and reconnect, and pockets of energetic particles would flare along invisible boundaries, space weather at the largest scale the sun can make. Farther still is the Heliopause, the boundary where solar wind pressure balances the local interstellar medium. It is a contact surface between two plasmas, not a wall of matter, and it can be wrinkled by changing conditions. The interstellar medium presses back with its own plasma, neutral gas, dust, and magnetic field, and that pressure is not constant. The Sun moves through a local cloud and the heliosphere's shape responds, compressed in one direction, extended in another. Voyager 1 crossed that heliopause in 2012, marked by particle and magnetic field changes. The spacecraft entered interstellar plasma, but it did not exit the Sun's gravity, and it did not leave behind every trace of solar influence. The crossing was inferred from multiple instruments telling the same story in different languages. Solar particles dropped, galactic cosmic rays rose, and the magnetic environment shifted, subtle, technical clues that together formed a dramatic boundary. Crossing into interstellar space means entering the local interstellar medium, the gas and dust between stars. It does not mean leaving the solar system in the gravitational sense, because gravity is not a bubble that pops. We return to the central question about endings, because the heliopause is an ending that misleads. It feels like a border because it is measurable, sharp and dramatic, and because it carries the romance of the word interstellar. But the Sun's gravity does not care about plasma boundaries, and it does not stop where the solar wind stops. Gravity does not end at the heliopause, and it does not end at the Kuiper Belt either, because it fades smoothly with distance. Fading is the theme of this chapter, and it is also the honest geometry of nature. Many boundaries in astronomy are defined by thresholds we choose, where a pressure balances, where a population thins, where a timescale changes. To keep the definitions honest, we separate three boundaries that get conflated. There is a magnetic and plasma boundary, a gravitational boundary, and a population boundary, and each one answers a different version of the word home. The magnetic and plasma boundary is the heliopause, and it is shaped by solar activity in the interstellar environment. It shifts over time, and it can ripple like weather, because the solar wind itself varies with the solar cycle. When the Sun is more active, it launches faster streams and eruptions that propagate outward for months and years. Those changes can push the heliopause outward or allow it to relax inward, slow breathing on a scale of billions of kilometers. The gravitational boundary is the Sun's Heliopause, the region where the Sun dominates over the galaxy's pull. It is not a crisp sphere, but it sets a scale for long-term ownership, especially for objects on extremely wide orbits. The Heliopause is a concept born from the three-body problem, a reminder that belonging depends on competition. The Sun is orbiting the Milky Way, and the galaxy's tidal field steadily tugs at distant trajectories. The population boundary is the distribution of bound objects, especially the Kuiper Belt and the inferred Oort Cloud. This boundary is statistical, and it may have no clean edge, because formation and scattering create gradients rather than fences. The Kuiper Belt is a thick disk of icy bodies beyond Neptune, roughly from the low 40s to about 50 AU. It is structured by resonances, migration history, and scattering, and it preserves the solar system's early dynamical scars. Resonances matter because Neptune's gravity can lock objects into repeating orbital rhythms. Pluto's 3-2 resonance is the famous example, but it is part of a broader architecture, patterns that reveal how the giant planets moved in their youth. New Horizons made that region real with Pluto and Arrokoth, and it made the edge feel tangible. Pluto's active nitrogen cycle proved distant worlds can stay complex under weak sunlight, because internal heat and volatile chemistry still do work. The visuals linger on Pluto's blue haze and layered atmosphere, backlit by a tiny sun. Glaciers of nitrogen creep across basins, and mountains of water ice rise like bedrock, geology operating in slow motion at 40 times Earth's distance. Arrokoth showed gentle accretion and preserved chemistry, implying the belt can store fossils. Its contact binary shape suggests low-speed assembly, and its reddish surface hints at complex organics formed by radiation and time. The student dust counter hinted the belt may extend or fade more than our catalogues show. Dust impacts are a different kind of census, because they can reveal populations too small and too dim to be seen as individual points of light. Even so, the Kuiper Belt is still close compared with what the comet record implies. The Oort Cloud, if real, expands the solar system from a disk into a vast shell, and it forces us to think in distances that stop feeling planetary. The scale difference is the documentary's final shock, and we state it without softening. The Kuiper Belt is tens of AU thick, and the Oort Cloud may reach tens of thousands, turning the solar system into a faint sphere of potential. If Neptune is about 30 AU, the main Kuiper Belt is only a few tens beyond that. The outer Oort Cloud may extend to 50,000 AU, and perhaps toward 100,000, depending on how the Sun's grip competes with the galaxy. That is not a bigger belt, it is a different category of space. It is a region where the Sun is a bright star and the galaxy becomes a co-author, writing slow edits into orbits over millions of years. Historically, the idea of such a cloud emerged from a puzzle, not from a photograph. In 1950, Jan Oort argued that the distribution of long-period comet orbits implied a distant reservoir, an unseen source that could refill the inner system. A simple analogy keeps the ratio legible while staying precise. If Neptune is a step from the Sun on a scaled walk, the Kuiper Belt is a short hike beyond, still within the same neighbourhood of familiar landmarks. On the same scale, the Oort Cloud is a journey across continents, with the Sun's influence thinning the whole way. The point is not drama, but orders of magnitude, because physics changes when distances become that extreme. This is why the Kuiper Belt feels like the edge on a classroom map. It is the farthest place we have visited up close, and it is where the planetary diagram stops, because drawing farther begins to break the page. But the Oort Cloud reframes that edge as a doorway, because it is not a line, it is a volume, and its density likely fades outward rather than ending, which means the edge becomes a question of how faint is faint enough. Transition. We now use comets to close the evidence loop, because comets are the only routine messengers from that distance. Long-period comets arrive on near parabolic orbits, barely bound to the Sun when first measured. Their semi-major axes imply they spent almost all their lives far beyond the planets, drifting in cold storage where sunlight is negligible. When one finally falls inward, it changes character quickly, as if waking from deep time. Ice sublimates, dust lifts, and a coma blooms around a nucleus only a few kilometers wide, small bodies turning into spectacular temporary atmospheres. Their arrival directions are nearly isotropic, coming from all over the sky. That geometry is hard to fake with a disk-like source, and it points to a spherical reservoir, a shell that surrounds the planetary plane rather than sharing it. Each long-period comet is a return address we cannot read directly, but we can infer statistically. The Oort Cloud remains unseen, yet it keeps sending mail, and every orbit we compute is a partial stamp from the outskirts. The triggers that send that mail are not mainly the planets, but the galaxy. Passing stars and the galactic tide talk distant orbits, lowering perihelia over deep time until a once quiet object becomes a visitor to the inner Sun. The galactic tide is gentle, but it is persistent, and persistence is power. Over millions of years, it can reshape an orbit's orientation and eccentricity, small accelerations accumulating into a decisive change in where a comet dives. Passing stars add randomness to that steady pull, and the solar system's history includes many such flybys. Some encounters would have stirred the cloud, and others may have stripped it, reminding us that the outskirts are not protected. That means the solar system's outskirts are porous, not sealed. The same forces that inject comets inward can also strip objects outward into interstellar space, turning former members into unbound wanderers with no Sun at all. This is where the Heliopause returns as a contrast, because it is a boundary we can touch. Voyager crossed a plasma line while comets trace a gravitational gradient, and the two stories describe different kinds of outside. The Sun's domain is therefore not one thing, and our definitions decide the story's ending. If we define the solar system by solar wind, Voyager has already left, and the Heliopause becomes a headline-worthy frontier. If we define it by gravity, Voyager is still deep inside, and the Oort Cloud is still part of home. If we define it by objects, the boundary becomes a probability field, where membership is a matter of statistics and timescales. The Heliopause offers a formal gravitational scale, but it is not a lived border. It marks where galactic tides can compete, and where long-term stability becomes uncertain, because tiny nudges can accumulate over cosmic time. The Oort Cloud likely occupies that contested regime, making the boundary a timescale question. An orbit can be bound today and effectively unbound over billions of years, which raises an unsettling thought about permanence. What does it mean to own a region of space if ownership depends on waiting long enough? At the farthest distances, the solar system becomes less like a territory and more like a temporary arrangement. The terrifying conclusion is not only that the Oort Cloud is huge, it is that the solar system may not have a clean edge at all, and that our instinct for borders may be a habit from living on a planet. The Kuiper Belt has an apparent outer drop in objects near 50 AU. but even that edge may be incomplete. Dust data and detached objects hint at a fading structured outskirts, where discovery is limited by faintness and bias. The scattered disk already blurs the belt's boundary, with bodies on elongated orbits shaped by Neptune. Beyond that, the inner Oort Cloud may overlap in definitions and in origin, because scattering and capture can populate multiple reservoirs. So the solar system's map becomes layered, not bounded. Planets dominate inside, Neptune sculpts the disk, and the galaxy edits the farthest orbits, and each layer has its own physics of stability. Transition. Having separated the boundaries, we ask what future observations can actually change, given the distance and faintness. Next-generation sky surveys will expand the census of distant trans-Neptunian objects and comets. Better statistics will test claimed orbital patterns and reduce selection bias, which is crucial when we infer structure from a few rare detections. Improved orbital arcs will clarify which objects are detached, which are scattered, and which hint at deeper reservoirs. The goal is not a single discovery, but a cleaner distribution, because distributions are where formation histories hide. Direct detection of Oort Cloud bodies remains brutally hard, because reflected light is tiny and motion is slow. Even large objects would be faint against crowded star fields, and their apparent drift could be lost in the background. Stellar occultations offer one strategy: catching brief dips when an unseen body crosses a background star. Occultations trade brightness for geometry, but they demand enormous monitoring, precise timing, and careful filtering of false positives. Infrared limits can constrain large, cold bodies by their thermal emission, but the emission is weak and distant. Non-detections still matter because they bound what can hide, narrowing the range of possible populations without ever seeing a single object. Future missions could push farther than Voyager with better power and communications, but travel times remain long. Even a fast probe would take centuries to reach Oort Cloud distances, and that reality forces humility into mission design. So the near-term path is mostly astrophysics, not spacecraft. We will infer the farthest structure by statistics, dynamics, and rare events, translating faint patterns into a model of a region we cannot yet image. We revisit the documentary's keywords to keep the frame consistent. The Kuiper Belt is planetary science and exploration, made real by NASA flybys and telescopic surveys, and it remains a laboratory for early solar system chemistry. The Oort Cloud is astrophysics and inference, revealed by comet orbits and galactic perturbations. The interstellar medium is the environment pressing on the sun's bubble, shaping the heliosphere's size and the character of its boundary. The cosmic abyss here is not exotic matter shaping local dynamics. Dark matter is not central to Kuiper Belt or Oort Cloud structure at these scales, because the dominant forces are ordinary gravity, plasma pressure, and long-term perturbations. The darkness that matters is observational and physical, because most of the solar system is unlit. Most of its mass in small bodies is unknown, because distance hides it, and because faint objects are easy to miss even in careful surveys. This is the final answer to the central question, stated as a reframing rather than a slogan. The Kuiper Belt is a distant frontier, but it is not the sun's true footprint, and it is not the last chapter of the map. The Oort Cloud, if it exists as inferred, is the real scale of the sun's domain. It is so large that home fades gradually into interstellar space, and the distinction between inside and outside becomes a matter of definition. The Heliopause is a dramatic crossing, but it is not the end. It is a weather boundary inside a much larger, quieter gradient of gravitational influence, and gradients do not give you a single moment to point to. We end where we began, with the handheld map that lies by compression. On that map, the Kuiper Belt looks like the edge of everything, because it is the farthest labelled ring, and because labels stop where certainty stops. In reality, that ring is only the doorway to a volume of darkness that may reach nearly halfway to the nearest star. The solar system stops being a set of worlds and becomes a dissolve, a thinning of membership across enormous scales. What remains is a neighbourhood defined by gravity, time, and the galaxy's quiet pull. The farther out you go, the less the word border applies, and the more the word gradient fits, because nature rarely draws straight lines. Voyager keeps going, comets keep arriving, and the sun keeps losing dominance by degrees. The ending is not a line in space, but a slow surrender of certainty, measured in faint signals and long orbits. We began with the comfortable lie of the planetary map, where Neptune looks like an ending, and distance looks like empty space. Up close, New Horizons turned that emptiness into geology, showing Pluto's nitrogen glaciers, haze skies, and unsettling hints of interior heat. Arrokoth then whispered an older story, a gentle merger preserved in deep freeze, while the Kuiper Belt's resonances and scattered orbits recorded Neptune's migration like grooves in ice. Yet even that structured wilderness, with its sharp-looking drop near 50 AU and its puzzling excess dust, kept refusing to be a clean border. The Heliopause, dramatic as Voyager's crossing was, proved to be only the edge of solar weather, not the edge of ownership. And then the scale truly broke, because long-period comets arriving from every direction forced a three-dimensional answer, a vast Oort Cloud inferred from statistics, shaped by passing stars and the galaxy's steady tide. In that outer regime, the solar system stops being a place we can photograph and becomes a probability field. Porous, erasable, and defined by timescales more than miles. We also left some mysteries deliberately unresolved, because the outer solar system is still teaching us humility. Sputnik Planiscia's true origin, impact cold trap, deep mass anomaly, or a planet-wide reorientation, matters because it decides whether Pluto is a rare accident or a template for distant activity. The energy budget behind Pluto's youth remains a live debate, balancing nitrogen convection, sublimation cycles, possible cryovolcanism, and the stubborn possibility of a long-lived ocean beneath rock-hard water ice. The Kuiper Belt's edge may be real, or it may be a trick of what we can detect, blurred by detached objects, scattered survivors, and that dust counter that keeps insisting there is more. Planet 9 may be a genuine sculptor, or a mirage made from biased surveys, and the rumoured 2026 atmosphere on a tiny distant world may be a bound blanket, or merely comet-like breath. But those uncertainties don't weaken the story. They sharpen its central revelation. The farther out we go, the more the solar system becomes an argument about evidence, definitions, and invisible structure. At the end of our journey, the Kuiper Belt stands as the last region that feels like a neighbourhood, because it still contains worlds with surfaces, seasons, and histories we can read. Beyond it, the Oort Cloud is not another belt, but a haunting shell, possibly tens of thousands of AU thick, where the sun's grip thins into negotiation with the Milky Way. It is the difference between a frontier you can map and a frontier you can only infer, between a disk of relics shaped by Neptune and a sphere of potential comets shaped by everything that passes nearby. That is the terrifying scale difference, and it is also the emotional difference, because it forces us to admit that home has no single wall. The solar system is layered, with boundaries that overlap, shift, and fade, and the outermost one is less a line than a slow surrender of certainty. So where does our neighbourhood actually end, and what is hiding out there beyond the Kuiper Belt's doorstep? The honest answer is that the end depends on what you mean by end, but the most meaningful boundary is the one that can still send us messengers. By that definition, the Kuiper Belt is the last place we can visit and recognise, while the Oort Cloud is the sun's real footprint, a dim reservoir whose existence is written in the orbits of long-period comets. What hides out there is not a single object waiting in the dark, but a vast population, mostly unseen, constantly reshaped by stellar flybys and the galaxy's tide, and therefore never fully ours. The edge is not a cliff, it is a gradient, and the farther you travel, the more the solar system becomes less like territory and more like influence. If that feels unsettling, it should, because it changes what it means to belong to a star. We are used to thinking the sun rules a tidy system of planets, then a belt, then nothing, but the truth is stranger and quieter. The Kuiper Belt is a chapter we can read in photographs, in resonances, and in the scars and glaciers of distant worlds, while the Oort Cloud is a chapter we can only reconstruct from fleeting visitors that blaze and vanish. Between them lies the most sobering lesson of scale, that our familiar map ends not because the solar system ends, but because our senses do. And beyond the last image, beyond the last catalogue, the sun's domain dissolves into the interstellar medium, not with a boundary stone, but with diminishing light, widening distance, and the galaxy's patient pull. In the coming years, that pull will become part of the science, not just the poetry. Deeper surveys will stretch orbital arcs, reduce selection bias, and tell us whether the farthest objects truly cluster, or merely seem to, and whether a hidden planet is shaping the outskirts. Occultation campaigns and infrared limits may finally tighten the Oort Cloud census, even if direct images remain out of reach, and Comet statistics will keep refining the invisible architecture. New missions may chase interstellar visitors or send faster probes outward, trading decades for data and turning the faintest hints into constraints. Each improvement will not simply add dots to the map, it will clarify which edge we are talking about and which edge matters for understanding our origin. Because the terrifying difference between the Kuiper Belt and the Oort Cloud is not just that one is bigger, it is that one is knowable in the human way, and the other is knowable only through inference and time. One is a landscape, the other is a shadow cast by gravity across a light year of space. And when you ask where the solar system ends, you are really asking when the sun stops being the dominant storyteller and becomes just one voice in the galaxy's crowded choir. The final twist is that the end is not a place you reach. It is a relationship that weakens until the next star's gravity matters as much as ours. So keep watching the comets, keep questioning the edges, and keep an eye on the surveys that are slowly turning darkness into data. So where does our neighbourhood actually end, and what is hiding out there beyond the Kuiper Belt's doorstep? The end is not a wall at 50 AU, but a fading gradient, and what hides there is the Oort Cloud, an inferred comet-supplying shell that marks the sun's most fragile reach. The Kuiper Belt feels like the edge because it is the farthest chapter we have read with our own eyes, but it is still only the beginning. Far beyond it, the solar system ends the way light ends at dusk, without a line, only with distance, and with the quiet realization that gravity too eventually lets go. If you want to know where home really stops, follow the next generation of sky surveys and treat every new comet orbit as a clue from the sun's invisible frontier.